on an oscilloscope.
All right, well, that was super cool, and I was not expecting it, so that was a fun surprise. Welcome everyone to the Neutrino parallel session. It's half past, so I think we better go ahead and get started right on time. I'm Elizabeth Worcester from BNL. I work in accelerator neutrino oscillation, and I'm your convener for this half of the session. All of our talks in this session are the 12+3 variety, so it's going to be tight. So everybody try and stay on schedule. I will give speakers 2-minute and 1-minute warning. I'm going to try to use the annotation feature so as not to interrupt the flow of your talk. So you'll see like a little text box appear on the screen. And then at 12 minutes, I'll pop up verbally. Speakers, if you can share your video, we're asked to try to do that to make it a little more human. But if you can't, that's okay. Attendees, if you want to ask questions at the end, the best way to do it is to use the raised hands feature. If somehow that doesn't work for you, you can try to use the chat. In my experience, sometimes that goes by kind of fast, so I might miss chat questions. So the raised hand is the preferred feature. I'm supposed to tell you we have 35 participants online in the meeting right now, and growing by the second. So I think we better go ahead and get started. Marilisa, can you go ahead and share your screen?
Yeah, sure. So, okay.
Okay, great. We see it.
Oh, I can also.
Do you want to go to full screen if you can?
My video and then go. Okay.
Okay, very good. All right, so our first speaker is Marilisa DeSerio, speaking about neutrino physics at the ICHEP experiment at CERN. Go ahead.
Yeah, thank you. So good afternoon, everybody. So in my talk, I will show the updated neutrino physics performance studies and the progress in the detector design of the proposed ICHEP experiment at CERN. So given the current status of the current picture of high energy physics showing at the same time the triumph of the standard model and evidence for the existence of physics behind the standard model, two complementary approaches can be exploited to search for new physics. We can probe the energy frontier, which is the task of high lume LHC and future colliders, and or probe the so-called intensity frontier, searching for light particles with masses the GeV scale with very weak couplings to standard model particles. ICHEP, which stands for Search for Hidden Particles, is a proton beam dump experiment proposed at CERN using the beam dump facility, which is under design in the SPS North area. The main physics goals are the search for particles belonging to the so-called hidden sector, and I will show the potential of ICHEP in searching for heavy neutral leptons, as well as study neutrino physics with special emphasis on tau neutrino physics and search for a light dark matter. Following the recommendation from SPSC and CERN Research Board, the collaboration has finalized the comprehensive design study report at the end of 2019. The beam dump facility is a general purpose fixed target facility at the SPS, sharing the SPS already existing TT20 transfer line with a beam that would be deflected into a new line as sketched in this picture. The BDF team has completed a comprehensive design study at the end of last year with a detailed description of the feasibility studies, which have been carried out over the past 3 years, as well as prototyping and the evaluation of safety aspects. This is the current layout of ICHEP for 100 GeV LC protons will impinge on a target, high density target in spills of 1 second. The target is followed by a hadron stopper and a magnetized muon shield, which has a task of bending out of the detector acceptance beam-related muons. The scattering and neutrino detector, the SND, is the detector devoted to neutrino physics and search for light, dark matter. The hidden sector detector has been designed to search for visible decays of possible hidden particles occurring in a long decay vessel, 50-meter long, located immediately downstream of the scattering and neutrino detector. In 5 years of data taking, with about 2 × 10⁻20 protons on target expected, we expect more than 10⁻18 heavy mesons and more than 10⁻16 tau neutrinos to be produced at the beam dump. A few more details on the main elements. So the target will be made of blocks of titanium, zirconium, molybdenum, so followed by blocks of pure tungsten for a total thickness of about 12 interaction length. And that's been specifically optimized for heavy meson production. The target is followed by a hadron stopper that filters out hadrons and the electromagnetic component emerging from the target, while muons will be deflected by a magnetized muon shield, which is able to reduce the flux in the detector acceptance by about 6 orders of magnitude with respect to the initial muon flux. This is a scattering and neutrino detector. The main physics goal is the measurement with unprecedented statistics of the interaction cross-section of all neutrino flavors, with a special emphasis on tau neutrino physics, as well as search for light, dark matter. It consists of a magnetized target, which is made of bricks of emulsion tungsten, similar in their structure to the bricks used in the OPER experiment, interleaved with planes of electronic trackers based on scintillating fibers. The submicrometric space resolution of nuclear emulsions allows the tau lepton decay to be reconstructed, typically occurring a few hundred microns downstream of the neutrino interaction vertex. And the magnetic field allows for the measurement of the sign of the charge of the daughter particles produced, thus making it possible to distinguish tau neutrinos from tau antineutrinos. The target is followed by a muon identification system instrumented with RPCs and iron filters. Immediately downstream of the GSND, the decay vessel is located. It is completely surrounded by a veto system based on liquid scintillator to efficiently suppress the background. And here in this slide, you can see a sketch of the main background sources that have been taken into account in the evaluation of the sensitivity of the experiment to the search for hidden particles. The hidden sector spectrometer is equipped with a stir tracker, which has been designed to reconstruct the decays of hidden particles occurring in the decay vessel. It also shows a timing detector, which is required to efficiently suppress the combinatorial background, an electromagnetic colorimeter, and a muon system. An intense activity of prototyping and testing has been carried out over the past few years. In this slide, you can see some of the detector prototypes which have been built and tested, as well as a small-scale replica of the ICHEP target. In 2017, the collaboration proposed a dedicated experiment with the aim of measuring the differential chain production cross-section, including the cascade production contribution, which is expected to be relevant in ICHEP, given the high density target that we plan to use. A test measurement has been performed at the SPS H4 beamline in 2018, and a lot of effort has been made in developing and optimizing analysis tools to reconstruct interaction and decay vertices in a high density and high background environment. The density of track segments in one single emulsion film being as large as 10 to the 5 per centimeter squared, and capability of reconstructing vertices in such a quite tough environment has been fully successfully demonstrated. Coming to the physics performance, as I said before, the main goal of the SMD is the measurement of the interaction cross-section for all neutrino flavors. In this second table here, you can see the expected numbers of tau neutrinos and anti-neutrinos according to the different tau decay channels. So overall, in 5 years of data taking, we expect to collect about 10,000 tau neutrino and anti-neutrino events, which means a sample which is a factor of about 1,000 larger with respect to the only sample available, which amounts to only 9 events measured by the donut experiment, which has also provided the only measurement available of the cross-section with a statistical error of 33%, which could be significantly improved with ICHEP data. Neutrino, tau neutrino and anti-neutrino cross-section also offer the possibility, the unique capability of measuring the structural functions F4 and F5, which are typically not accessible through muon and electron neutrinos due to the fact that they are multiplied by factors that are proportional to the square mass of the charged lepton. Moreover, we expect to collect more than 200,000 charmed hadrons produced in neutrino-induced interactions. Again, a sample which exceeds by more than 1 order of magnitude the statistics already available from previous experiments. Anti-neutrino-induced charm production is also sensitive to the strange quark content of the nucleon, and reduction of the order of factor of 2 on the uncertainty of the S-quark distribution is expected to be achievable with ICHEP data in the range of the Bjork variable between 0.03 and 0.35. The SMD and ICHEP can also probe, investigate the existence of light, dark matter by detecting the electromagnetic shower initiated by the recoil electron in the scattering of light matter particles in the SMD target. Target bricks can indeed act as sampling calorimeters, as you can see in this picture taken from the OPERA experiment. Moreover, the submicrometric accuracy of nuclear emulsions offers a topological discrimination of the signal against background, which is mainly due to quasi-elastic interactions of electron neutrinos with the soft pion not identified at the vertex. The plot shows the sensitivity for assuming 5 years of data taking, as you can see from the plot, in the range between a few MeV or C squared to a few hundreds MeV or C squared. We expect to improve current limits by 1 order of magnitude. One of the main goals of the experiment is the search for hidden particles, and specifically the search for heavy neutral leptons. The search for right-handed sterile neutrinos, which would be Majorana partners of the active neutrinos as postulated by, for example, the neutrino minimal standard model. These particles could explain neutrino masses through the C-cell mechanism, as well as also baryon asymmetry, and the lightest of the three particles could be also a dark matter candidate. In ICHEP, such particles could be produced in the semi-leptonic decays of heavy mesons and detected through visible decays in standard model particles, as for example, this golden channel in muon and pion. The plot shows the sensitivity as a function of the mass, and as you can see, and a region that ICHEP will be able to probe an improvement of up to 3 orders of magnitude is expected. So in conclusion, ICHEP is a proton beam Doppler experiment proposed at CERN to probe the so-called intensity frontier. It has a quite rich physics program, including heavy neutral leptons, light dark matter searches, and neutrino physics with unprecedented sensitivities. The BIMDAM facility and ICHEP experiment comprehensive design study reports have been finalized in December last year, and in next month, further steps will be defined by the collaboration on how to proceed. That's all. Thank you.
Thank you very much. Do we have any questions? You can raise your hand in the Zoom. Going. All right, I don't, there's one. Sunny, go ahead.
Hello, can you hear me?
Yes, go ahead.
Okay, sorry, I was talking with mute. So ICHEP experiment seems to be very interesting experiment, and I just wonder the experiment is funded or not?
No. We will have to define next steps in next month. Considering the output of the European strategy and the implementation that will be done at CERN in September, the medium-term plan of CERN should be made available, and then the collaboration will define steps, further steps to proceed.
Okay, can you tell us the budget of this experiment?
If I can tell you what?
Yeah,
sorry?
can you tell us the budget, the cost of the experiment?
So it's 150 millions for the BDF, which is the main point, let's say, to be overcome. So it's for the BIMDAM facility, which is the first element, key element that we need to go on.
Okay, good luck.
Thank you.
Thank you very much. I think we better move on to the next talk. So Francesco, can you go ahead and share your screen?
Sure. Can you hear me?
I do hear you. You're a little bit faint.
Okay, maybe now is better, right?
Yeah, yes, that's much better.
Okay, definitely. Okay, so just. Can you see also the slides now in full screen?
Yes, this looks good. So our next speaker is Francesco Terranova speaking about INUBET. Go ahead when you're ready.
Okay, thank you very much. So I will give a brief report on the achievement that we got, especially in the last year for INUBET. I remind you that INUBET is a project that started in 2016, funded by the European Research Council with the leadership of Andrea Longin. And then very recently, I would say in April 2019, INUBET has also been approved at CERN as a CERN experiment in the framework of the CERN Neutrino platform. And this is the reason why the title now is NP06. NP06 is actually the name at CERN together with the standard name from the ERC. The collaboration has grown significantly in the last 2-3 years. We are now about 60 people from 12 institutions and five countries. And the aim of INUBET is to design, so this means that it is an R&D, not yet a proposal for an experiment, to design a narrowband beam at the GeV scale to measure the flux and the flavor of neutrinos at source at 1% level, and to measure on an event-by-event basis the energy of the neutrinos with a typical precision of 10%. Is a new technology. We believe might be the right technology for a new generation of short baseline experiment to achieve a precision of 1% in the new mu cross-section and remove most of the biases due to the energy reconstruction in the final states for total and differential cross-section. Clearly, this is essential to lower below 3% the systematic budget of Dune and Hyper-K and enhance remarkably the discovery reach. And this is also the reason why the European strategy support so strongly this kind of research for INUBET, but in general for the reduction of the uncertainty of the flux. And we believe that it is the most natural follow-up of the current generation of experiment for cross-section. Now, the basic concept is quite simple. You probably know that all absolute cross-section are dominated now by the knowledge of the flux at source, and which in turn is dominated by the uncertainty on the simulation of the beamline and the other production data. The most simple way to get rid of all these systematics is just to measure the number of leptons that are produced in the decay tunnel, because there is a one-to-one relationship between, let's say, the positron that you produce and the electron neutrinos, or the muons that you produce and the muon neutrinos. INUBET in particular started looking at the production of the positron, large angle positron from the free body decay of the kaons, and instrumenting the decay tunnel in such a way that we can observe this positron over the year, especially I would say after the approval from CERN, we extended significantly the physics reach. Now we are working on monitoring the muon from the two-body decay of the kaons in the instrumented decay tunnel, and also transforming the hadron dump in a real range meter that is able to measure at single particle level the muons from the pions decay, which of course are the core of the new mu events in the detector. These ensemble of detectors are what we call in jargon a monitored neutrino beam. This is what how we dubbed this system. Now the beamline that I'm presenting, I would say, is probably the final version of the beamline of INUBET. It is based on 2 dipoles and 1 triplet that is located just after the horn. Every single part of the beamline is now simulated: the target, the transfer line, the proton dump, and also the hadron dump, where we are also adding this modification that I was mentioning before, plus a neutral shielding. Still, we wanted to implement this also in GEM4, not only in G4 beamline, because this is very useful to assess systematics, for instance, from neutrinos that are produced in the proton dump and for some reason they reach the neutrino detector. So there are still some work that has to be done, but most of it has been completed. Now let's go a bit more on the technical side. As you can imagine, if you run INUBET like you are running a T2K or NOVA, it will not work because the extraction is just, the proton extraction is just 10 microseconds. So you will get a huge number of particles all in the same time. And so this will saturate the detector that we want to put in the tunnel. So we need a relatively short extraction. In particular, we would like to have what we called, this is something that Andrea and myself proposed 5 years ago, we called it slow burst extraction. Essentially, there are small bursts of 10 milliseconds that are repeated with a frequency of 10 Hertz during the flat top. So not all the time, but just during the flat top of the accelerator. This system has been tested at the SPS at CERN in 2018, just before the LS2, just a couple of days of machine developments. At that time, we achieved 20 milliseconds, so we are in the ballpark of what we need, but not exactly. And then in this year, we implemented this scheme in the full simulation of the SPS. We played with mostly with the sextuple, and at least at the level of simulation, we were able to achieve burst between 4 and 10 milliseconds, which is exactly what we need for InnoBet. Of course, the demonstration with the real data will be done once the LS2 is over, so probably in 2021 or more likely in 2022. In parallel, we are re-optimizing the ORN for the new beamline using a genetic algorithm to find the right point in the phase space of the geometry of the conductor and the currents. And still we are working on the possibility of getting rid even of the ORN. In this case, you would not need a burst extraction, but you could work with a very slow extraction. This is unfortunately is not the scope of my talk. I don't have time to speak about this, but the big advantage of the static focusing option is that the particles are so how can I say, distributed interspace that in principle you could associate the neutrino observed in the detector with the corresponding lepton if the time resolution is good enough, is 100 picosecond, and this would be the famous tagged neutrino beam. InnoBet is not a tagged neutrino beam, is a monitored neutrino beam, but of course if this works, it might be upgraded to a target neutrino beam. Now, last year, we've made the final choice on the technology. Of course, we want to instrument the decay tunnel with something that is very cheap. It must be marginal compared to the cost of the beamline. And so we ended up with a longitudinally segmented calorimeter with the silicon PMs on top of the calorimeter to reduce the radiation damage. All this stuff was tested at CERN with a charged particle beam in 2018. At that time, we also tested the photon veto that is here located below, and the results were really very good. If you're interested in this, there is a paper that you can, it's just appeared in JInstant. You can find it in this link here. Now, the highlight of 2020, I would say the highlight of ICHEP 2020 for InnoBet, because this is the first time that we present these results in any conference, is the major improvement that we got on the identification and the monitoring of the lepton. From the technical point of view, the tough job was done already in the past. I'm speaking about a full simulation with the detector response, pile-up, event building, particle identification algorithm. All this has already been discussed. But of course, with the new beamline, we observed a significant improvement in the performance. This thanks especially to the re-optimization of the collimators and the shielding in the proximity of the first triplet. So for instance, for the positron from the free body decay of the kaons, for the first time we reach a signal to noise of 2.1 and an efficiency of 24% that is dominated by geometrical effect. That is, if you have a positron that goes straight in the axis of the decay tunnel, we cannot see it because it must touch the walls. So if it goes directly to the dump, this is not seen. But this is very good news because a geometrical effect does not contribute in a significant manner to the systematic. And then for the first time, we monitor muons, and we achieved a an impressive results, I would say, with signal to noise equal to 6.1 and an efficiency of 34% that at present we are exploiting mostly for the two-body decay of the kaons. We are also working on most of the results are optimized for Dune, I must say. We are also working for a version of this beamline that is optimized for hyper-K, where the energy, of course, is much lower, and this is our work in progress. So let's to the physics performance. The table that you see here is unfortunately a bit obsolete because this is the one of the previous version of the beamline. I think that after the optimization of the ORNA, more or less we will get the same results, but this is something that I cannot guarantee yet. So please take this table as preliminary. The following results are given under the assumption of having a 500-ton neutrino detector located 100 meters from the source, or if you like, 50 meters from the hadron dump. The beamliner is able to produce 10 to the 4 fully reconstructed new charge current events in about 1.5 years of data taking, and 80% of these events, the spectrum is here, correspond to events where the leptons really are in the decay tunnel, and then there is a correction of about 10% that comes from the decay of the kaons before, which means in the transfer line, plus the contribution from K-long, which gives essentially this low energy part that, of course, we will not use because probably in the real analysis for Dune, we will cut the very low energy region. Concern the neutrinos, the muon neutrinos, of course, the statistic is huge. We are speaking about 1 million of fully reconstructed new mu charged current events per year. So it's infinite from the point of view of cross-section. The flux is monitored using the range meter for the muons coming from the pi, and the instrumented decay tunnel for the muons coming from the free body decay, from the two-body decay of the kaons. On the other hand, the momentum bite of INUBET is very small, as at the level of 10%. So this means that there is a very straightforward correlation between the position of the interaction vertex of the neutrino and the energy of the neutrino. It's like an off-axis experiment, but instead of having the detector off axis, you have a single detector and you just span the position of the neutrinos. And we were able, we dubbed this technique narrowband off axis techniques. I don't think we invented it because more or less this is in literature, but the results are really impressive, I would say. For instance, for 3GV muons, we are able to provide on event-by-event basis, that is for any single neutrino, the energy with a precision of 10%, which get worse, at least in this configuration, to 20%, so a factor of 2, if you go to 1 GV. The final step, or the next step for the project, as you can imagine, will be the construction of a real demonstrator, which means a real 2-meter long tunnel. Of course, the real experiment is 40 meters. This is a prototype, but you will see 2 meters of instrumented decay tunnel at CERN by the end of 2021. We are working on the mechanical design and the procurement of the material. And in general, I would say that INUBET is on schedule in the sense that the design phase is over, the simulations are nearly completed, and we are going to build the final demonstrator. In my opinion, the work that we are doing right now, it is as important as the construction of the demonstrator, is really to show that the systematic budget for the flux is really 1% or below. This is work in progress. We are using practically the same technique that T2K or other long baseline experiment are using. That is, we are adding the observable coming from the instrumentation of INUBET as additional priors to the rest of the simulation in order to defeat the flux systematics and of course the information of the energy in order to reduce the cross-section systematic on a final state interaction. So at the end of the story, I think we will build the demonstrator and do this study in 2021. And then once the COVID emergency is over and also the machine are online at CERN, most likely by 2022, I believe, then we will test the demonstrator with the charged particle beam at CERN. And that's all.
All right, thank you very much. We're over our question period, so I think probably I better encourage people to ask questions to you offline so that we don't get too far behind. But thank you for the very interesting talk.
Okay.
Our next speaker, Brant, can you go ahead and share?
Yeah, sure. Can you hear me?
Yes.
Okay, great. All right. I apologize. I don't have a camera on my laptop. So thanks for the opportunity to speak. I will talk today about hadron production measurements we make at Na61, also known as SHINE. Okay, so today, briefly, I'll give you an overview of long baseline neutrino oscillation experiments that we provide data for. And then I will talk about a leading systematic uncertainty in these experiments, the neutrino beam flux uncertainty. And then I will tell you about our experiment, Na61, or SHINE, and the measurements that we make there to help constrain these uncertainties. And then I'll tell you about an upgrade we're undergoing right now and some future measurement possibilities. Okay, so long baseline neutrino oscillation experiments have given us many prominent results over the past several years. There's lots of great results still coming out of active long baseline experiments like T2K and NOVA. And then there's some great future long baseline experiments planned like Dune and Hyperkamiokande. And the focus of these experiments is going to be resolving the last remaining issues in the neutrino oscillation picture, but also really precisely measuring all of the oscillation parameters. And in order to achieve the level of precision that they aim for, they're going to have very tight control over all the systematic uncertainties. And one of these such uncertainties is the neutrino beam flux uncertainty, which enters into cross-section calculations and oscillation parameter results. So this is the uncertainty associated with the flavor content of the neutrino beam generated for the experiment. And as you can see in this cartoon here, the neutrino beam content is going to directly depend on the hadronic interactions in the target and also the target beamline facility. So yeah, this content is going to directly depend on primary interactions that happen both in the target or secondary interactions that happen in the target and in horn elements or support elements for the beamline or elsewhere. And if you try to estimate your initial neutrino beam flux, you don't use any kind of hadronic interaction constraint data, you can have really large uncertainties on your resulting neutrino flux. And this becomes a large uncertainty to deal with. So how do we reduce this uncertainty? Well, we make hadron production measurements. We can do this in two ways. We can either take thin target measurements, investigating pertinent reactions for different experiments, whether that might be 30 GeV protons on a thin target, thin carbon target in the case of T2K, or 120 GeV protons on carbon for the NUMI beamline. And then, so yeah, you can select your thin target material and your beam type, and then study the hadron production off of that target type. You can also take replica target measurements, as we call them, where we mimic the neutrino beam creation interaction. We take either a copy of the neutrino beam target or the target itself and put that in a beamline, use the same beam species and energy, and directly measure the hadrons produced off of that target. And just to show you the impact that these measurements can have on beam flux estimation, this is the beam flux uncertainty at Super Kamiokande, and you can see that going from just using thin target data in the dashed line here down to using replica target to these two sets of lines here can reduce the beam flux uncertainty by several percent in the interesting region. So these are important measurements to make. And now let's talk about the facility where these measurements were made, called Na61 or SHINE. So Na61 is a fixed target experiment at CERN's SPS, located in the north area. It's in the middle of the LHC ring, as you can see here. SHINE stands for the SPS Heavy Ion and Neutrino Experiment. We've got a big multifaceted physics program. There's a strong heavy ion program. We also do studies for cosmic ray physics. And then there is this neutrino flux constraint measurement part of the physics program. Na61 is a really versatile detector in that it can receive many different types of beams. It can get primary 400 GeV protons directly from the SPS, or those protons can be directed into a secondary production target, and we can get second protons, pions, and kaons anywhere from 13 to 350 GeV. So lots of beam particle species options. For target materials, we can basically take thin target data using any target material that's easy and safe to handle. And then we can also use full neutrino experiment replica targets as we've done in the past. This is just a picture of the detector here. Let's look at another view of the detector. So the beam comes in on the left here, and then the detector starts here. So Na61 is made up of 8 time projection chambers primarily. This gives us 3D tracking and also DDX measurement in the detector for particle identification. 2 of these TPCs are inside vertex or superconducting magnets called the vertex magnets that give us momentum determination. We also have Cherenkov detectors upstream of the detector, which tell us the species of the beam particle coming into the detector. In the case of a secondary beam especially, this is really important. And then we have 3 beam position detectors, which give us the trajectory of the particle on its way into the target. And then we also have time of flight detectors, which help us do particle separation in the beta block crossing regions. And we have a forward calorimeter also. This is used for heavy ion physics mostly. So yeah, these are our capabilities for neutrino experiment measurements. This is our thin target holder here. So this is just a picture of one of the carbon targets that we used in the past. But this thin target holder can, be outfitted with beryllium or aluminum or iron or yeah, any nice target material that we can get our hands on. And these are some of the replica targets that we've made measurements with. This is the 90 centimeter T2K target up here, upstream of our first TPC. And then this is the NUMI medium energy target that we took data with back in 2018. And then down here, you have a typical event that you might see in one of these interactions. You have the beam coming in from the left here. The target is here where this vertex is located. All the tracks are meeting up, and then we have tracks bending in the magnetic field as it passes through the detector and through our TPCs. Okay, so let's talk about some recent results. We'll go over thin target reactions first. I'll show you production cross sections, and then we'll talk about charged hadron yields and neutral hadron yields also that we've measured. First, I should present a definition. There can often be some confusion in our field with what we mean by production, inelastic, and quasi-elastic. So here, when I say inelastic cross section, I mean the total cross section with the elastic portion subtracted off. So it's going to be composed of the production and the quasi-elastic cross section. And then the production cross section is the inelastic cross section with the quasi-elastic term subtracted off. Okay, so here are some of our recent results. These are production and inelastic cross sections of many different reactions at various energies. So here we have pions on carbon, aluminum, and beryllium, kaons on carbon and aluminum, and then protons on carbon, aluminum, and beryllium at various energies, mostly 60 and 120 GeV. And so these cross-section measurements are used to weight hadron production and correct neutrino flux predictions when doing beam Monte Carlos for estimating neutrino flux content. Another recent result is one of our charged hadron yield analyses. So yeah, we get the ID of a produced particle in our detector using our TPC's DDX and also the momentum of the tracks that we measure. And then we can bin up our accepted phase space and perform a DDX fit in each of these bins. And then we could get multiplicities for protons, pions, kaons, electrons in different p theta bins. And yeah, this is one of the results down here. This is a slice of angular acceptance. And so you can see for this range of momentum, for the red data points here, our measurements really disagree with all of the models listed here. So we use the data, or the data is used to inform the models, retune them, and improve them. And then those models again go into the Monte Carlos estimating the beam flux at long baseline oscillation experiments. We also do neutral hadron production yield studies. So we can select positive and negative track pairs in our detectors and extrapolate them back towards each other. And if they're close enough, we can enter them into an invariant mass calculation. And then we get, once again, a doubly differential. So a P versus theta yield of K0 shorts, lambdas, and lambda bars. And then here you have some recent results again compared to various models. Okay, and there are lots of ongoing analyses too. These are just some of the analyses that have been released lately. There is a beam survival probability study going on to try to measure the production cross-section of protons on the T2K replica target at the T2K beam energy. There's also a thin target proton on carbon and proton on aluminum at 60 GeV analysis, which is very mature, and this is going to give differential yields for charge and neutral hadrons, like I just presented. And then an exciting analysis, which is beginning now, is the analysis of the protons on NUMI medium energy replica target. So this is data taken at the NUMI beam energy, and this will also give differential yield measurements for both charged and neutral hadrons when it is complete. Okay, the next thing I want to talk about is improving the acceptance at the experiment. So back in 2017, my group was involved with constructing and installing 3 new time projection chambers right in the beam line. So previously, this part of the detector was uninstrumented. So you can see from the acceptance plot up here, so this was a 120 GeV beam interaction, and the acceptance really gets very poor and drops off completely at low angle and high momentum. But with the addition of these new detectors, now we can, we've improved our phase space coverage all the way up to the beam momentum here at 120 GeV. And it's got a really cool, what we call a tandem field cage design, where we can reject out of time tracks right off the bat. So with the inclusion of these new detectors, we can do even more exciting analyses. Right now, I'm working on an analysis of protons on carbon at 120 GeV. This is the NUMI beam material and energy, so it's an important reaction to study. I'd like to have a charged hadron analysis completed in the next couple of months. A neat thing is that the increasing of this forward acceptance leads to, I think, the potential for maybe elastic or quasi-elastic cross-section measurement directly, which would help us to rely less on models for correction. This is a list of other data sets that are waiting to be calibrated and analyzed. So I'm working on this one here, and then we had full forward acceptance for these last 3 reactions. So we have a lot of data that we are analyzing, and lots of results to come. Also, we are undergoing a big upgrade right now. We're increasing our data acquisition rate by an order of magnitude, and we're also replacing the TPC front-end electronics with the old Elise electronics. We're developing a low energy beamline to push our lowest energy down to 1 GeV, which is really exciting for making future measurements for other experiments. And then we'd like to develop a tracker to help do vertexing in long target reconstruction. We're going to resume data taking in 2021 or 2022. Okay, so in conclusion, neutrino beam flux is leading systematic uncertainty for long baseline experiments, but NA61 or SHINE is capable of taking relevant data to constrain this neutrino flux. The thin and replica target data results for several pertinent reactions have been published and are currently used in oscillation analyses. And we would love to get the Dune replica or a Dune target when the design is finished and take some data with it. So stay tuned, and thank you.
Thank you very much. We have time for questions if anyone wants to raise their hand. Last chance. All right, I'm not seeing anything. Thanks a lot.
Okay, thanks very much.
Our next speaker is Budimir Klichek talking about ESS new SB. Can you go ahead and share?
Yes, let me share my screen. Can you see it?
Yep,
Yeah,
it looks good.
perfect.
Go ahead when you're ready.
Okay, right. So hello, everyone. My name is Budimir Kliček. I work at the Ruđer Bošković Institute in Zagreb. And today I will talk about the ESS USB project. So the ESS USB project is a design study for an experiment to measure CP violation at second neutrino oscillation maximum. So this is the basic idea of what we want to do. As you know, CP violation in neutrino oscillations is manifested by the fact that oscillation probability for neutrinos is different than oscillation probability for antineutrinos in vacuum. In particular, in ESS USB, we want to look at the electron-neutrino appearance and muon-neutrino beam. So our plan is quite simple. First, we will run with muon-neutrinos and look at the electron-neutrino appearance, and then we will run with the muon antineutrinos and look at the electron antineutrino appearance. And then we will compare the two samples and see if the oscillation probabilities are the same or not. The special thing about this project is that we want to measure all of this at the second oscillation maximum. So I'm going to try to explain why. The basic idea, the good thing about the second oscillation maximum is that the CP violation signal there is about 3 times larger than the CP violation at the first oscillation maximum. The problem there is, of course, you have to go either further away, exactly 3 times further away, and then you get the flux which is 9 times smaller. Or you can reduce the neutrino energy 3 times, and then you get the cross section, which is at least 3 times smaller, or you can go even below the charge lepton production threshold. So the optimal case actually depends on the systematic error, which we assume is similar at the first and the second oscillation maximum. The main point is that the larger signal at the second oscillation maximum is less obscured by systematics, but you have to make sure that you still have enough statistics to measure anything. So if the signal at second maximum is not obscured by larger statistical error, then second maximum is better. And for this, you need to have an intense neutrino beam. And also it's important that theta 1,3 is large enough, because otherwise you would get no appearance events. It should be noted that with 0 systematic error, which never actually happens, first maximum is always better because you get more statistics. So can we go to the second maximum? Well, as it happens, a very intense proton linac is in construction near Lund, Sweden. And theta 1,3 seems to be large enough according to our GLOBS simulations. So the ESS proton linac is designed as a very intense source of spallation neutrons. It will have 5 megawatt average beam power, which is peak at 125 megawatt during the pulse. It will have 14 hertz repetition rate and a duty cycle of 4%, meaning that 96% of the time it will not accelerate protons. And here we see our chance to add additional proton cycles, which we can use to produce neutrinos. The designed energy of the protons is 2 GeV kinetic, but it can be upgraded up to 3.5 GeV. And this machine will actually be capable of producing 2.7 times 10 to the 23 protons on target per year, which put in the perspective is actually 450 milligrams of protons per year at 95% the speed of light. So it will actually accelerate the macroscopic amount of matter to ultra-relativistic speeds. So we want to modify the ESS linac to produce neutrinos. And for that, we need to build a new target station, which will be optimized for neutrino production. We need to dig out the underground hole, which will host our new detectors. We want to increase the proton energy to 2.5 GeV kinetic, because this will give us a better CP violation sensitivity. And we want to double the linac rate, so that neutron people still get their protons and we get our protons. One of the problems is that the ESS proton pulse is too long. So we need to build an accumulator ring to compress these 3 millisecond proton pulses to about 1 microsecond, because otherwise our magnetic horns would melt, because the current because the current would be too long. But also that we found that the atmospheric neutrino background would be too large for CP violation measurement with long pulses. And of course, we must not interfere too much with the neutron program. So here you can see the energy distribution of neutrinos we expect to have from the ESS optimized for neutrino production. The beam would be quite pure muon neutrino beam, which is very good for the CP violation measurement, but could be a problem for the calibration, because we need to use the small NUI contamination to measure the electron-neutrino interaction cross-section. Our near detectors, so the baseline is to have a 0.5 kiloton water Cherenkov of detector as a near detector, and immediately upstream of that we would have a super FGD-like detector of 1 to 4 tons target mass. So the super FGD-like detector means a detector which is a collection of small scintillator cubes which can be read out semi-independently. And we are considering a possible addition of the Ninja-like water emulsion detector, which we can put in front of the super FGD and use to have a really good discrimination between electron muon neutrinos, and we can also measure the neutrino topology with it. Concerning the fire detector position, our baseline is the Garpenberg mine, which is about 540 kilometers from neutrino source, which corresponds more or less exactly to the second oscillation maximum. And the alternatives we are considering is the Zingruen mine, which is 340 kilometers from the source, which still covers a lot of the second oscillation maximum. And there was an idea to have half of the detector at Garpenberg and half at Zingruen. But as you can imagine, this is the most expensive option, so I don't think it will happen. Concerning the fire detectors, our baseline is to have 2 large water Cherenkov detectors, which with 270 kiloton fiducial volume each. The signal would be read out by 20-inch PMTs, and we would have about 80,000 of them for the 2 detectors. And this is assuming 30% of optical coverage. Having such big detectors, they can be used for other purposes like proton decay, astroparticles, galactic supernova neutrinos, solar neutrinos, atmospheric neutrinos, and so on. So the geological studies in the mine are already underway. And here you can see the technical drawing of the Zingruen mine with possible positions of our fire detectors. The physics performance that we expect from all of this is shown on this slide. So since we are in the second oscillation maximum, we have a little dependence on neutrino mass hierarchy. We are covering the delta CP values range at 5 sigma up to 60% of the range, and we are quite accurate down to 6 degrees at no CP violation values. And all of this is actually by assuming a very conservative systematic errors on signal background, which is 5% on signal and 10% on the background. It is important to mention that there are already ideas about synergies between with our proposed modification of ESS Linac. So one idea is to take the muons from the decay channel and decay tunnel and put them in a storage ring, and then you get new storm. Or you can additionally accelerate these muons, put them in a larger storage ring, and then you get a neutrino factory. Or even more advanced, you can separately accelerate positive and negative muons and then collide them, and then you get a muon collider, which is quite a good Higgs factory. All of these studies are actually underway, and there is a dedicated series of workshops which is regularly organized to explore these new synergies, additional things that could be done with the ESS USB proposal of the upgrade of the ESS Linux. So all of this was made possible by the EuroNewNet cost action, which is now finished. It actually finished at the beginning of this year. But this cost action was, among other things, used to apply for the Horizon 2020 project, which was approved. And we got a budget of 3 million euro from the European Commission, and we are 15 participating institutes from 11 European countries, and including CERN and ESS. So concerning the possible schedule, so we are optimistically planning to start data taking in 2035. Right now we are here. We are in the design study. Then we need to do the TDR. Then we need to find the international agreement to actually build this thing. Then we plan to construct and start data taking. So to conclude, ESS USB aims to observe CP violation in neutrino oscillations and the second oscillation maximum. Yes, for this we are planning to use the ESS Linux, which will be the most powerful proton accelerator in the world. We are already considering what kind of additional physics we can do with the proposed modifications. We can use our large fire detectors for many other things, especially the astroparticle physics program. And all of this was made possible by the COST Network project and the ESS USB H2020 design study. So thank you for your attention.
Thank you very much. We have time for questions. I see Sunny. I'm going to unmute you. I think you have to do it too. There you go. Go ahead.
Okay. Can you go to your sensitivity plot?
Yes.
Yes, here. So this is, so did you assume 2 detectors with 270 kiloton each here?
Yes.
Okay. And 10 years of data taking?
Yes.
And the distance is 540 kilometers. So I don't quite understand why your sensitivity is not as good as T2HKK, considering you have twice, more, detector volume and half the distance compared to T2HKK. So basically you have 8 times of more statistics compared to the second, hyper-K second detector in Korea. But it looks like the sensitivity of yours is similar to us. So I don't quite understand.
Well, it's hard to actually answer this question because I can't see the expected sensitivity of hyper-KK.
Okay, so have a look, but I don't quite understand since you have 8 times or more statistics according to your numbers.
I don't know. I'm not sure which kind of systematic error did hyper-KK assume.
So for hyper-K, we basically used T2K, systematics. So it's not really, we invented much better, systematics. So, but how about you?
Well, as you can see here, it's 5% systematic on signal and 10% on the background.
5%?
But I believe, yes.
So I think it's similar.
But it isn't for the hyper-K, I remember something like 4% on everything.
For the systematic?
Yes.
But in this case, if we
assume 4% systematic error, then we are much better, of course. But with time, we are going to kind of lower our systematic error. So you can expect these plots to become better and better as the project progresses.
But for the second Okay.
Yeah, so let me interrupt you guys. I mean, doing these kinds of sensitivity comparisons is always super fraught, and doing it online in front of a bunch of people is probably impossible. So you guys should probably talk offline.
Yeah. Okay.
Okay.
Thanks.
Thanks again for the nice talk. I think we'll move on to our next talk from Akitaka Ariga about phaser new at LHC. So if you can unshare, Budimir.
Yes.
You can go ahead and share. Okay, looks good. Go ahead when you're ready. Oh, wait, you're muted though.
Okay.
There you are.
So let me start. Thank you very much. And I'm going to talk about phaser new, which is a new experiment at LHC to study high energy neutrinos. I'm Akitaka Ariga from University of Bern. The phaser experiment is for such experiment at the LHC. So conventional experiments like ATLAS or CMS looked for the new particle emitted in transverse direction with respect to the proton beam. However, not much attention has been paid for the forward particles in these red arrows. We noticed that there is an intense neutrino beam here, and possibly there is a beam of long-lived particles, LLPs, here. So far, regrettably, there is no experiment sought neutrinos at the LHC. So therefore, we propose the phaser experiment, both for LLP searches and neutrino experiment. The phaser new particle searches was approved by SAN in March 2019, and phaser new neutrino program was approved recently in December 2019. There is a phaser general talk in the BSM session on Friday by Michaela. If you are interested, please have a look. This is the layout of LHC high energy neutrino beam line. I put a double quotation on the beam line because this layout is not designed for neutrino beam line itself, but it works as a high energy neutrino beam line. Following the proton-proton collision in ATLAS, there will be forward meson. Bunch of meson will be produced, and some of them decay into neutrinos. And then the charged particles will be deflected away by the LHC magnets, and neutral hadron will stop in the rock. And only neutrinos and possible long-lived particles can go straight through the rock. And there is a disused service tunnel here, and we replace the phaser new immersion-based neutrino detector and the phaser magnetic spectrometer. So phaser sites are placed 500 meters away from the ATLAS collision point. In this way, we can exploit the intense neutrino beam with almost negligible cost for infrastructures. The expected neutrino spectra are shown here. As you can see, the phaser new spectra fall in the region where there is no data available. For example, for nu E, so we can fill the gap between accelerator data and IceCube measurement. And for nu E and nu tau, we can provide points at the highest energy ever. The neutrino beam is very much collimated. This is a size, and the neutrino beam size is of the order of 10 centimeters, so that the small detector makes sense for this measurement. Phaser new measurement is not simply just a neutrino measurement, but we are opening a new domain of neutrino research. The phaser new spectra compared to the other accelerator neutrino beams are shown here. And so as you can see, the spectra, phaser new spectrum is the highest high energy frontier of man-made neutrinos. The neutrinos are made by collider method. This will be exploited for the first time. so that we can study production, propagation, and interaction of high-energy neutrinos using this beamline. For the production, 14 TeV proton-proton collision is equivalent to 100 peta-electron-volt proton interaction in fixed target regime. So we can study prompt neutrino production at the peta-electron-volt scale. This will be a variable input for neutrino telescopes. We can study charm gluon PDF at high energy and then study intrinsic charm. We are also sensitive for the neutrino oscillation at delta m square around 1000 electron volts squared. And for the interaction, we measure the 3 flavor neutrino cross sections in unexplored energy range, study neutrino-induced heavy quark productions, and possibly study new physics effects in interactions. For this project, we carefully prepared, we studied the feasibility studies and performed the in-situ measurement in 2018. We placed immersion detector in TI-18 and TI-12 tunnels. There are 2 sites, symmetric position with respect to the Atlas interaction point. So this is a picture and this is immersion detector. We measured particle flux and angular distributions. And this shows the angular distribution, and there is clear peak of particles from Atlas interaction point, and there are secondary peaks from the LHC beamline infrastructures, but they are found to be very small. The flux, measured flux is listed here compared to the Fulka simulations, and we found the background level is low enough for neutrino measurements and consistent with Fulka expectations. More importantly, we demonstrated that the immersion detector can work at the actual environment. Following this result, we already performed the pilot run in 2018, aiming to demonstrate the feasibility of detection of collider neutrinos. The small detector, 30 kilogram immersion detector, was installed on axis of the LHC beam, and we collected 6 weeks of data corresponding to 12.5 inverse femtobarn. This is reconstructed data in the small volume, 2 millimeter times 2 millimeter times 10 immersion films. There are a lot of particles reconstructed, but there are muons and electrons, so that this will not bother our neutrino measurement. In fact, we successfully reconstructed some of neutrino interaction vertex. We are really excited about it. The size is 200 nanometer. We are performing a statistical analysis. We have analyzed effective target mass of 12 kilogram. Since the pilot neutrino detector doesn't have lepton identification, so the separation of neutral hadron background is a problem. For that, we applied tighter cuts. 11 neutral vertices were selected, and after BDT analysis to separate neutrino signal and neutral hadron background, we selected 3 events with a certain cut. With this, we found 3 events with 0.8 expected background. So in this sample, we expected a few signal events so that it is consistent with the signal plus background expectation. The p-value of background of only hypothesis is 0.05. So this result demonstrated the detection of neutrinos from the LHC. The detector design for next 4 years is here. The detector is called phasor new. This is a flavor sensitive neutrino detector. In the picture, neutrino come from right and enter to the phasor new detector. This is immersion tungsten detector. This is followed by the phasor spectrometer to identify muon charge, so that we will separate nu mu and anti-nu mu differently. The immersion detector is made of tungsten plates and immersion films. Immersion film is high precision tracker. And lepton identification will be done in the detector by the topology and kinematical measurements. So like this, tau express the decay topology. Moreover, we are sensitive to the charm and beauty production channels. So the detector is dedicated for the flavor physics studies. The neutrino energy resolution is expected to be 30%. The detector is small, just 1 ton detector, but we expect a lot of neutrino interactions of the order of 10,000 cc events during the run 3 from 2021 to 24. This is interacting spectra, and the mean interacting energy is about 1 TeV as shown here. We have currently a few different neutrino flux estimates with different hadron production generator implementations. So we have currently large uncertainty. So in particular, the decay, the neutrinos from the decay from charmed particles has large uncertainty. For example, for nu E, but that affects nu E and nu tau flux estimates. And for nu E, they could be different by 1 order of magnitude among different hadron production generators at higher energy, above 1 TeV. So therefore, we are working to update neutrino flux estimates, and in particular, the work is in progress for quantifying and reducing the systematic uncertainties by creating a dedicated forward physics tune with PTR8 using forward data. The expected cross-section sensitivity is shown here. So we will be able to put several points during the in the region where there's no data is available for nu E and nu mu, and we'll be able to put a single point for nu tau. We have a series of additional physics studies, and maybe we can study furthermore, we can test some of the new physics models like light gauge boson. The experimental site is being prepared. This is a phaser site last year, and this is March this year. So the site is cleaned up, and trench for the phaser detector is prepared. So we will transport 1 ton detector over the LHC beam pipe. Therefore, we need some protection of LHC beam pipe, which is cooled down at liquid temperature. So the protection is already installed, and it is ready to for the experiment. So phaser nu is the new experiment and the first experiment with collider neutrinos, and it's opening a new domain of physics research. The detection of neutrinos are demonstrated by the pilot run in 2018. We are going to take data in run 3 and collecting 10,000 neutrino events with flavor sensitive detector. Furthermore, we are discussing for neutrino measurement at the high luminosity LHC error. Thank you very much, and this is a collaboration.
Thank you very much. Do we have questions? People can raise your hand in the Zoom. I'm not seeing any. I guess I have a question. Do you have thoughts on synergies between this and the oscillation physics program? Or is it really very different physics that you're looking at here?
So we can study neutrino oscillations, but the sensitive delta m square is about 10,000 electron volt squared. So it's relatively different from the other experiments, which look for standard or stellar neutrino oscillations.
Cool, thanks. Other questions? I'm not seeing any. Okay, thank you again. Our next speaker is Heng-Hee Liao, speaking about hadron-argon cross-section measurements in protodune single phase. So you can go ahead and share your screen.
Hi, first of all, can you hear me?
I hear you, yes.
Okay. I assume that you can see my screen sharing right now.
Yep, looks good. Go ahead when you're ready.
Okay, thank you very much for your introduction. So today I'm going to talk about the hadron-argon cross-section measurements in protein single phase. First of all, I will talk you about the final state interactions, and then our experimental setup, and then the cross-section measurement that we use for in protein single phase. And then we specifically focus on the pions and then proton interaction channels, and then their event selections. Nowadays, the neutrino experiments use complex nuclei as neutrino targets. And when hadrons, they are produced in neutrino interaction, they can reinteract with the nuclear medium before leaving the nucleus. This effect is known as final state interactions, FSI. It's an important effect in neutrino interactions that this effect can change the charge multiplicity of outgoing hadrons, as well as alternating their final state kinematics. In the final diagram plot here, without any involvement of the this FSI effect, this will be a CCQE event. But with the involvement of the FSI, this may not be true anymore. This effect is a very important element in neutrino event generators that we heavily rely on to unfold the reconstructed neutrino energy to the true neutrino energy. With the precise knowledge of the nuclear models, that would help us to get the precise measurement of the oscillation parameters. We do have many models, but however, we only have very, very limited measurement to do the validation. The main physics goal of the proton single phase is to measure the hadron-argon cross sections. By doing so, we can provide the critical information on hadron scattering in liquid argon, and then help better understanding of the FSI in neutrino-argon interactions. With the improved FSI model, we can reduce the systematic uncertainty on neutrino event reconstruction and then the neutrino signal selection. These are all very crucial to achieve the team physics goals. Quite recently, we are happy to announce that we have submitted our first paper on archive. You can see the archive link over here. For the setup of our experiment, we are locating at the CERN neutrino platform at the extension of the EHN1. So our detector is here, and then we enjoy the CERN H4 beam line, which with the known particles, namely pions, protons, kaons, muons, and electrons, with the momentum ranging from 0.5 to 7 GeV. Overall, we have collected more than 4 million of beam events. On the right-hand side, you see our main detector. That is the liquid argon time projection chamber. That I have labeled the size of our detector over here. And then the detector is divided by 2 volumes. This liquid argon time projection chamber will provide us the good tracking and then the calorimetry capability that allow us to do the hadron-argon interactions in great details. So the detector here is a cartoon plot showing you the detector is here. We have a series of beam line instrumentation that can tell us some information on the incoming particles. Here you can see there's a time of flight detectors that they tell us the time of flight information. You can see on the figure over here, time of flight as a function of momenta. Different red curves represents for different particle species, and then the color spot here showing you our real measurement. Together with the trend curve information, we know exactly which type of particles that are coming into our main detector. After the particles coming inside our detector, that we use the Pandora multi-algorithm to reconstruct the checks and showers. Here you see the blue checks here are the cosmic ray tracks, and then the purple one here is the reconstructed beam particles. Protons and pions, they are all very important to the neutrino interactions. So for the proton cross-section channels, we are interested in the inclusive cross-section. And then the subchannel would be the elastic or inelastic. So here showing you an event display of data that the proton comes in, that they have elastic scattering. You can clearly see the interaction vertex over here. This is the elastic scattering candidate. For the inelastic scattering event here, showing you another example that beam proton comes in, and then they have multiple proton being knocked out. For the pion cross-section channels that we are interested in the inclusive and then exclusive. Exclusive, we are specifically interested in the single charge exchange. Single charge exchange means that the charge of the final state pions will only differ by 1 unit from the initial pion charge. So here I give you an event display, an event candidate of the pion exchange events. So pion comes in, and then pi 0 being produced, and then pi 0 decay to 2 photon shells. That you can see a nice image over here by our real data taking. For the pion absorption channel is that the pion entering out TPC and then get absorbed. There's no pions in the final state. For the cross-section measurements that we have established entire framework for the cross-section calculation. The first method is called thin slice method. Is initially developed by the Larry experiment. We think there's a good approach, so we also use a similar approach. The principle of this method is that here showing you a cartoon plot that the liquid temperature chamber. So basically, we use the Y-to-Y spacing and then to sync slot the detector into very many small volumes. And then each thin step is considered as an independent measurement. So for each independent measurement, you ask a question that if there is any interaction. If no, then you put into the instant histogram beam. If until the very end that you have the interaction happen, you put so the ratio of these two histogram will provide you the profile of the cross section. Together with this scaling factor will be responsible for will be depending on the thickness of the target and then the density of your target. In our case, it's 100 bond for protein with single phase. With this, we were able to calculate the cross section for our measurement. The second method we have established is a so-called re-rating method. So the method is described as follows. So assuming you have a configuration of a Monte Carlo setting, then you will produce one Monte Carlo observable, but the only judge will be the data observable. You can imagine that you can tune many cross-section parameters, and then you can always compare with your data observable. By doing so, we can estimate the cross-section systematics as well as to use this method for the model-dependent cross-section calculation. For the pion event selection, the general feature of pions are there's no charge pion in the final state. I just remind you that there's a cartoon plot showing the pion charge exchange and then the pion absorption over here. For the event selection, that first of all, we use the convolutional neural network to tell us if the daughter particles are track-like or shell-like. On the bottom figure over here, that you see here is the CNN track-like score. If the particles are track-like, it will be close to 1. If the shell-like, it will be close to 0. The black dots here are our data points, and then you can see the purple histogram here will be the protons, and then the teal histogram here will be showing you the pions, and then the green one is for showers. So we make a cut to select tracks, and then the second cut we use is to use the proton chrometry information to identify to separate the pions in advance. So if the track-like particles are close to pion, the chi-square will be picking at around 1. You can see the purple color showing proton over here. And then you can clearly see that the pion is here. So we make a cut to select it to reject the pion events. This will be a general feature for pions. To separate the individual channels in advance, we look for the pi 0-like showers. And then we developed the 2 cuts to do that. First cut is to use the distance to vertex information to select the charge exchange candidate. You can see the green one here is for the pi0 shower. We make a cut and then to separate the 2 channels that I just mentioned. Similar profile can be, similar cut can be used, but use the profile of the number of hits. The overall performance that we have achieved, that the 67% for this exclusive channel, and then for purity is for 66%. There are many works that are ongoing is to optimize this event selection process. For the protons, we developed a cut to label the different types of interactions. That is to use the normalized track length. Normalized track length meaning that the reconstruct track length divided by the CSDA range. We get the beam momentum information from our beamline instrumentation and then converted it to the associated CSDA range. The CSDA range meaning the average track length of stopping protons. So protons travel and then they stop. And then if the proton stop, it will be picking close to 1. And then you see the tail here that are the inelastic scattering proton that they have interaction such that their track length is shorter than the stopping one. Here is showing you the overlay of our Monte Carlo simulation. You can see that we do have a good Monte Carlo simulation to describe the data observables. That you see the red one showing you the inelastic component, and the green one showing you the stopping proton, and then the blue one showing you elastic scattering. The overall agreement between data Monte Carlo is reasonable. And then these parameters that we plan to use this for the model-dependent cross-section re-rating. To conclude my talk, the final state interaction is very important to neutrino experiments. We are measuring the hadron-hadron cross-sections that will provide very important inputs to better understanding of final state interactions. And then there will be also help to achieve the Dune physics goals, and that will be beneficial to the entire neutrino community. We have a very fast process in good progress in both pion and then proton cross-section studies that we have established the entire framework. And then right now it's more focusing on how to make the selection better. We will deliver more important physics results, so stay tuned. Just to this all other nice talk from my protein colleagues. Thank you very much for your attention.
Thank you. Do we have questions? People can raise their hands. You all are a quiet bunch today. I'm not allowed to ask questions about this because I'm a Dune collaborator, but it was a very nice talk. Thank you, Henye. Our next talk is from Miguel Angel Garcia Paris on cryogenic instrumentation, also at ProtoDune. So can you go ahead and share your screen?
Yes. Can you hear me?
I can hear you.
Okay. Can you see my slides?
Yep, looks good. Go ahead when you are ready.
Okay. Hi, everyone. My name is Miguel, and in this talk, we are going to review the performance of the cryogenic instrumentation at the ProtoDune experiment. So let's start. As you all know, DUNE, that stands for Deep Underground Neutrino Experiment, is a new generation neutrino experiment that is being built right now at the United States. Its far detector is being formed by 4 liquid argon TPCs that will be placed inside 4 huge cryostats, as the one that you are seeing here in this slide. Each one of these cryostats will have 17 kilotons of argon mass, and they are expected to run for periods of time of 10 years long, even more, which means that during 10 years, the cryostats will remain closed. So in the meantime, we need a way of understanding what is happening with our detector. We need to know if everything is all right or if it isn't. So here is where the cryogenic instrumentation plays a fundamental role, because it is going to be our eyes and our hands inside the cryostat once it is closed. Of course, DUNE was not going to be built without previous experience, and we had before several prototypes, being ProtoDune the last one of them. The ProtoDune experiment, which you can see in this picture, has been operating during the last 2 years at the CERN Neutrino platform. It consists in 2 different modules, the dual phase one and the single phase one. And almost all parts that are conforming the Dune experiment have been tested here. And of course, among those parts, we find the cryogenic instrumentation. So what do we understand by cryogenic instrumentation? It is a group of different devices which aims to provide a comprehensive monitoring and understanding of the cryostat, the cryogenic processes, the detector, and the liquid argon itself during the different stages of the experiment, which will have a later impact on the physics results. Its ultimate goal is to ensure the long-time operational stability of the experiment. Here you can see an inner view of the single phase module of ProtoDune that you can see has a volume of 8 meters per 8 meters per 8 meters, which is pretty big. You can see highlighted the locations of some of the devices that form the cryogenic instrumentation. Here in red, you can see the location of the purity monitors. In yellow, the location of some of the temperature sensors. And in green, you can see the location of some of the cameras. We additionally have gas analyzers, level meters, and pressure sensors. And we are going to review all of them in the following slides. We're going to start speaking about the purity monitors that are miniature TPCs that can measure the electron lifetime in the liquid argon. If you have a look at this drawing, you can see that they have a cathode, they have an anode, they have a field cage, and they have an additional light source. When this light is fired, a cloud of electrons is generated in the cathode, and the electrons travels towards the anode. If we measure the charge generated in the cathode and the charge that reaches the anode, we can relate these measurements with the electron lifetime in the liquid argon. It is really important to have a precise knowledge of this value because it doesn't matter how powerful or how sensitive your liquid argon TPC is, because if the liquid argon is not pure enough, the electrons won't reach your readout system. Then your TPC will be basically blind. In the case of the single phase module, we have a vertical array of 3 purity monitors, each one of them at a different height. And in the case of the dual phase module, we have a vertical array of 2 short purity monitors and an additional long purity monitor at the bottom of the cryostat. We have them in different locations because we want to understand if there is any kind of relation between the location of the purity monitor and the purity of the liquid argon in that location. If we have a look now at the data, we can see that in the 3 cases, we almost reach or surpass the 10 milliseconds barrier of the electron lifetime, which means that from all the charge that is generated inside of our TPC, we are only losing a 10% of the charge, which is really good. Indeed, the Dune FAR detector's requirement is to have at least a 3 millisecond electron lifetime. So we are exceeding by far these requirements. Now we're going to talk about the temperature monitors. They are sensors, as the one that you can see in this picture, that can measure the temperature. And they were placed inside both cryostats for 2 different reasons. The first one was to monitor the cool down process and the filling process of the cryostat. These 2 steps of the experiment were probably the most critical ones, because during them, the highest temperature gradients appear inside the cryostats. And if those gradients had been too big, our detector could have been damaged. So we use the temperature sensors to understand and to control those temperature gradients. The second reason to have them is because they are providing precise measurements of the liquid argon temperature. And when we say precise, we mean at the millikelvin level. There is what we call fluid flow simulations that are trying to understand and reproduce the liquid argon behavior inside the cryostat. They are trying to predict the electron lifetime everywhere in the cryostat. So we are using these precise measurements as an input for the simulations. So for example, in the case of the single phase module, 2 vertical arrays of several temperature sensors were placed to measure the vertical gradient of temperatures in the liquid argon. And here you can see a comparative of the experimental data and the simulations. We can see that there is some agreement between both, but we still have some features to understand from the data. In general, the typical gradient that we have been observing is of the order of the 10 millikelvin, more or less, and it has been really stable during these last 2 years. Here you can see a plot of the stability of the gradient during 2 months, and you can see that it is basically flat. And having such a small gradient in a big cryostat as ProtoDune points that the liquid argon is being correctly mixed, which is really good because it does not provide the stratification of the liquid argon. Now, the cameras. 11 cameras were placed at each one of the cryostats. Some of them were placed in the liquid phase as those ones, and some of them were placed in the gas phase as this one. This one is placed in an acrylic tube that can be accessed from the outside of the cryostat and can be reoriented at any moment, which is really helpful. In general, the cameras have been really useful for us because they have been our eyes inside the cryostat. During the cool down process and the filling process, we use them to make sure that no part of the detector was damaged or even misaligned. And during the operational time of the experiment, we use them to monitor the high voltage systems, for example, looking for possible sparks in the ground planes, and to monitor the different movable parts of the experiment. In general, each time there was something going wrong inside the cryostat, we use them to try to locate the source of the problem. So that is why they have been so important for us. Here I'm showing you a picture of one of the purity monitors of the single phase module after the filling process. And here you can see a picture, an inner view of the fill cage of the dual phase module during the filling process. Now, the gas analyzers. Gas analyzers are commercial hardware modules, as the one that you are seeing here, that measures the amount of a contaminant in the argon gas. As we have told before, we need to have the purest argon possible. And the gas analyzer are continuously monitoring the amounts of contaminants in order to get so. We need to have less than 100 parts per trillion of oxygen and water, and we need to have less than 1 part per million of nitrogen, because if we have more, the physics can be compromised. Here you can see a simplified view of the cryogenic circuit of protodium, and the argon gas exits the cryostat through these gray lines. Here is where the gas analyzers are connected, and here is where the measurements are made. Finally, we are going to talk about the pressure sensors and the level meters. The pressure sensors are used to measure the pressure inside the cryostat, either absolutely or relatively. Here you can see a picture of the pressure sensors of the single phase module. And the level meters are used to measure the liquid argon level inside the cryostat. Here you can see an inner view of the dual phase module in which you can see a long level meter here and a short level meter here. Pressure and liquid argon level may seem like pretty standard variables, but they have a really high impact on the physics results. So it is really important to have them under control. For example, the absolute value of the pressure inside the cryostat sets the absolute value of the temperature of the liquid argon. And at the end of the day, the electron drift velocity depends on the absolute value of the liquid argon temperature. In the case of the dual phase module, the electrons travel parts of their path toward the readout system in the gas phase. So we need to characterize as accurately as possible this gas phase. We need to know exactly which is the distance that the electrons travel from the liquid argon surface to the readout system. And for example, in the dual phase module, in the readout planes, we have placed level meters that are sensitive to displacements of the order of 100 micrometers. And you can see in this plot here. At the end of the day, the pressure, the temperature, and the liquid argon level are variables that are dependent among themselves. So any kind of variation of any of them can generate changes in the other two. So this is why it's so important to have them under control, because we don't want the physics to be compromised. Here you can see the liquid argon level during a pressure cycle, and you can see clearly how the level grows as the pressure grows, and then the level goes down as the pressure goes down. This is something that cannot happen during that data taking period, for example. Now, before finishing, I would like to show you a few examples of how we have used the cryogenic instrumentation during these last 2 years. As we were talking about the readout system of the dual phase module, the dual phase needs the surface of the liquid argon to be as flat as possible. So any kind of disturb in the surface of the liquid argon is not good for us. And in the dual phase module, for example, we have used the cameras to locate bubbles appear in the surface of the liquid argon. Here you can see the bubbles appear in the surface, and here you can see the bubbles appear in the surface. It has helped us to understand how to fight these bubbles. As I told at the beginning, the temperature sensors were used to monitor the filling process, and they were used, for example, to measure the liquid argon level as the filling process was going on. And they are being used to monitor the liquid argon level as the emptying process is going on, as you can see here and here. In general, all the cryogenic instrumentation is really sensitive to any kind of variation that can happen in the cryogenic processes. So each time we saw a a drop like that in the temperature data or in the purity data, we knew that something was going on, and we could act quickly to solve the problems in the early stages. This is why the cryogenic instrumentation has been so important for us, because it has helped us ensuring the long-time operational stability of the experiment. So that's all. As we have seen, the cryogenic instrumentation of the Protodune experiment has successfully operated during the first whole run of the Protodune experiment, and it has been extensively used during all the parts of the experiment, since the filling process up to the emptying process. And it has played a fundamental role ensuring the long-time operational stability of Protodune. And of course, it will play the same role in the Dune far detector. What is next now? The cryogenic instrumentation has been already improved, and it will be tested again in the second run of the Protodune experiment before its final deployment at the Dune far detector. And that's all by my side. Thank you very much for your attention.
Thank you very much. Do we have questions for Miguel? People can raise their hands. I see no questions. We have a second though. Maybe I can give you a chance. Do you want to say a little bit about what the improvements are for the run 2 cryogenics?
Yes, sure. For example, here, if you have a look at this plot of the purity, it might seem that there is some kind that it exists a stratification because there is relation between the location of the purity monitor and the purity that is measuring. It seems that the top purity monitor is measuring higher purity than the bottom one. For the second run of the Protodune experiment, we are trying to figure out if this is real or if it is not. So we are going to exchange the electronics from both purity monitors to see if this is something real that is happening, or this is something that is not real because of the electronics. This is only just one example.
Great, thanks. Okay, we have a question from Wencheng. I think you can go ahead and unmute yourself.
Yeah, this is Wenqing. I couldn't find the hand previously. My question about the long-term stability of your cameras and the sensors, they are so important. Are you going to replace them if they fail, like 5 years in the road?
For the moment, no one of the sensors has shown any kind of fail of the temperature sensors, and I think no one of the cameras has shown any kind of fail. The cameras that are placed in the liquid argon phase, they are not expected to run for a long time. They are just needed to run for a couple of years, but for the moment they have not failed. And the ones that are placed in the gas phase, the good thing of them is that as they can be manipulated from the outside of the cryostat, they can be exchanged or replaced at any moment. So this is something that does not worry us really much about the future.
Okay, thank you.
You're welcome.
All right, last chance for other questions. Okay,
I have a question. Yes,
can
you remind me what's the cause of the bubbles?
You mean the cause of the bubbles?
Yes.
Okay, let me see if I have a picture of that. I think I don't have. In one of the corners of the joints of the fill cage of the dual phase, there was a kind of a space in which the argon gas was trapped and then it was released toward the surface. And this is what was causing the appearance of the bubbles. So
it's very easy to fix it then.
Yeah, it was easy. Indeed, we were making some kind of pressure cycles in which after raising the pressure a little bit, all the bubbles were released, and then we had periods of time without any kind of bubbles.
Did you see the same in the phase, I mean, the double phase?
No, this was seen, the bubble problem was seen in the double phase.
Yes.
And in the single phase, as far as I know, we haven't seen it, but I'm not completely sure because this is something that does not worry us in the case of the single phase module.
Okay, so all right.
All right, thanks very much for the nice talk. I think we should go on to the next speaker. The next speaker is Kenneth Long talking about NewStorm. So can you go ahead and share your screen? Very good, I see it. There we go. Looks good. You can go ahead when you're ready. Although I don't hear you yet if you're trying to speak. Yeah, you're still muted.
There we go.
Yes, there you are. Go ahead when
now
you're
we
ready.
should be good. Okay, thank you very much. So it's a pleasure to have the opportunity to present NewStorm, which I think I would like to convince you is a unique facility for neutrino physics, but also as a place where one can do accelerator R&D for muon collider. Okay, so here we go. What NewStorm is a small muon storage ring, as was already described. In particular, it is using technologies which are only slightly beyond state of the art. So the goal is to create the muon beam by shooting protons onto a target, collecting pions with a horn, and then injecting the pions into the production state of a storage ring. The pi to mu transition is happening as the pions pass down the production straight. At the bend, only the muons are circulated. The pions are directed into a dump. On the first and subsequent passes, the decays are producing neutrinos. In the first pass, you predominantly have the pion decays producing new mu's. In subsequent passes, you get new e's and new mu's democratically from the muon decay. You can instrument that with a detector close by, where you can make precise neutrino cross-section measurements, and you can have a far detector to measure the sterile neutrinos, or to search for sterile neutrinos, if that is required beyond the Fermilab short baseline neutrino program. So the goals then, the scientific objectives, or at least the neutrino science objectives of NewStorm are written there. So percent level neutrino cross-section measurements. Of course, one of the particular features is the large rate of nu E and nu E bar you can get from the muon decay, and therefore one seeks to measure with great precision and with sufficient statistics to look at double differential cross-sections of nu E and nu E bar. And of course, one can make a sterile neutrino search. To do that, we really need to deliver a normalization, in particular of the flux at the less or 1% or better level. We believe we can do this by instrumenting the storage ring. Of course, the muons are going around many times, and therefore there's many chances to measure the muon flux. We can look at the decays, so we can measure the electrons and positrons coming from the decay, and therefore we think we can calibrate the flux at that level. If we know the energy of the beam and we know the energy distribution in the storage ring, we know the energy spectrum of the neutrinos very accurately, because of course the Michel parameters from the muon decay are known with great precision. So we really believe we can make precise prediction of the neutrino flux sent to the detectors. A key feature I've outlined is that in the pi to mu transition, there's a very bright flash of muon neutrinos, and I'm going to show you that on the next slide. So what you see here is the neutrino spectrum, which has been estimated from a stored muon beam of 3.8 GeV circulating in the ring. What you see on the left-hand side is the flash, neutrino spectrum you get from the first turn. The solid dots are coming, so here was a stored, sorry, we were capturing pi plus. So we get a large flux of nu mu from the decay of the pions producing the muons. You can also see contributions from kaons and from the muon decays themselves. I think the key thing here is that there's a very large rate of muon neutrinos from the pi plus decay, and separated from that, there's a strong contribution of the nu mu's from the kaon decay. In subsequent turns, the neutrino spectrum you get from the decay of the nu plus is shown here, so that the black dots, there's the spectrum that you get from the mu plus, and the red dots are from the the nu mu bar from the mu plus decay. I just draw this line on to draw your attention to the height of this peak. So the pion flash in the first pass is very large indeed, but we're getting a very good flux of nu E's from the muon decay. Okay. I think one key thing, the shape of the spectrum, as I said, is very well known. We want to be able to store muon beams as a function of energy. So we want to be able to vary the energy. And this means that we can use the shape of that spectrum to calibrate the energy response of the detector. Okay. So if we would make an instrumentation such that there's a far detector, a distance of say 2 kilometers from a stored muon beam of 3.8 GeV, and we also instrument a near detector, we can make sensitive searches for sterile neutrinos. I've taken these figures from the publication from a while ago, and what they demonstrate is that for the allowed region that is coming from LSND, one is able to exclude that at the 10 sigma level. I think it's not the 10 sigma exclusion that one should focus on. I think one should look at that statistical weight as the power of the apparatus, and therefore one has a possibility to make really sensitive searches for sterile neutrinos should that be required after the SBN program. I don't have to explain to this audience that the searching for CP violation in long baseline experiments requires a good knowledge of the cross-section of the detectors, the cross-section of the neutrinos. The absence of such knowledge can lead to systematic uncertainties in the oscillation parameters, and perhaps more pernicious, if the cross-sections aren't known, you can get biases in the neutrino parameters that you estimate, which cannot be removed because they're intrinsic in the data and you cannot remove them by fitting various samples. So you need to make precise measurements of neutrinos. So in revising the design or the specification for the storage ring, we wanted to make sure that we could make the best possible measurements of neutrino cross-sections. So one way to look at this is to look at the compilation of data of neutrino cross-sections for as a function of energy. And of course, we note that there are different contributions, both in the neutrino and in the antineutrino fluxes. And there's a competition as a function of energy between the quasi-elastic, the DIS, and the resonance regime. And in principle, one wants to make measurements across that region in order to separate the contributions. Of course, high energy beams cost you more money. So we wanted to limit that range from the upper end. And if you look at the place where there is significant contributions from different processes, perhaps you want to look at measuring cross-sections in the range 0.5 to 8 GeV. We then considered the detectors. So people are developing very sensitive and very high precision detectors, both for June and for Hyper-K. So now I think if you imagine that you can use these things to measure more of the hadronic final state and to constrain the kinematics of the event, we convince ourselves that a reasonable specification would be that we would want to be measuring over the range, say 0.3 GeV to 6 GeV. So now we're assuming that we're going to have a detector which is capable of measuring Q squared and W, or at least 2 parameters of the event. And now we want to therefore store a muon beam such that we can vary the stored muon energy up to 6 GeV. So what we've done is taken a specification for the stored muon beam energy is that it shall be variable between 1 and 6 GeV. That's actually quite a challenge for the accelerated design. So as part of the CERN Physics Beyond Colliders study, there was a feasibility study of executing NuStorm at CERN. And I'm just showing you the outcome of that study. The NuStorm ring, which was redesigned in order to store this range of momentum, is shown here. Those of you that know the CERN site will recognize that the west area here, so it's on the French side of the west area in land which is owned by CERN, but which is not presently developed. Extraction is coming from LSS5 from the SPS, and the proton beam is then transported through existing and new tunnels onto the target, and eventually the pions are collected and injected into the storage ring. A new detector hall has been positioned in the study at this point here. We've arranged that it's transverse to the beamline such that in the pion flash, one is able to use the off-axis technique to vary the neutrino spectrum that you're getting from the two-body decay of the pion. And we also noted that in a suitable distance, about 3 kilometers away, there is a place where a far detector could be placed in order to make the sterile neutrino search. Of course, one of the focuses here is on measuring the neutrino cross sections, and I pull out an old figure of a compilation of the neutrino cross section data. On the left hand side, you're looking at the CCQE, nu mu and nu mu bar cross sections, and on the right hand side, there's nu e and nu e bar. So at the time when we made this plot, there were no measurements in this kinematic range. Now there are 1 or 2, but I think the key opportunity for NuStorm is to use the flux of neutrino events, electron neutrino events, in order to make precise measurements across this plane. And of course, in order to do that, we need to deliver a flux precision at the 1% level and a large data set so that we can look at the double differential cross section. I think in this regard, there's a strong synergy in the physics with ENUBET, and this is something which would be lovely to discuss going forward. Okay, so the Physics Beyond Collider study, the goal there was to find a credible proposal for siting the facility at CERN, and this was, I think, achieved. What we found was that the SPS can deliver the beam. There is a place where we can put it which does not interfere with existing tunnels, and therefore it is possible to implement NuStorm at CERN. We identified challenges, in particular the magnets in the decay ring, and we need to do a detailed evaluation of the radiation protection and other issues around the target. So I just want to comment on the possibility for the development of a muon collider. I emphasize here that because a muon is a fundamental particle, in principle, the discovery reach of a 14 TeV muon collider is similar to that you would get from a 100 TeV proton-proton collider. So there is interest in developing the technology to deliver a muon collider, and how NuStorm could contribute is through the targeting capture. The large aperture ring in particular is a demonstrator for large aperture acceleration that would be required at the to deliver the muon collider. In particular, one could do a 6D cooling experiment to follow the muon ionization cooling experiment that run at Rutherford Lab, and the storage ring instrumentation would be very important too. I note that in the European strategy, there is the recognition that the measurement of neutrino cross sections is an important contribution to the long baseline program, and perhaps that's a thing that Europe could develop. And I've stolen a slide from Andrea Long from the Neutrino conference, where he is emphasizing the possible synergy between the implementation of ENUBET at CERN and NuStorm. And I think this is something we need to discuss going forward. Then these are my conclusions. NuStorm, when we implement it, will be a unique facility. It will be able to deliver percent level electron and muon neutrino cross sections. It will be able to deliver exquisitely sensitive sterile neutrino searches, and it can serve in particular a 6D cooling experiment and become a muon collider accelerator testbed. We've established the feasibility study through the Physics Beyond Colliders study group. And as a step towards the muon collider, I think we demonstrate that muon beams of this kind can be used to deliver particle physics. Thank you very much.
Thank you very much. Do we have questions? People can raise your hand. I see one from Francesco. You should be able to go ahead and unmute yourself.
Okay, yes. I just want to stress once more the point that Ken raised, that is, if you look at the first part of NuStorm, the transfer line, most of the features that are requested for ENUBET are also the same for NuStorm. I see that the current beam line of ENUBET is practically the same length of NuStorm. So this is a great opportunity for a synergy for the two projects. It's just a comment.
Great, thanks. Other questions or comments? I'm not seeing any. Maybe you could say what are next steps towards actually realizing this? Like what practically needs to happen next?
Well, I think so two things I think are the immediate thing. I think we need to engage with the SNOMAS process. I think there's lots of expertise in the Americas that would be extremely valuable to develop this program. Separately, I think the vehicle through which we can develop the activity comes in two forms. One is, as Francesco said, forging an appropriate collaboration with INUBET. The other, I think, is engaging with the Emerging Muon Collider collaboration in order to create the conditions where we can do the design study that we need. So we've demonstrated feasibility, but we have not carried out the work that would allow you to know how you would do it in detail, or what the detailed cost would be, or where you have to break into the existing rings and stuff like that. So I think those are the two things we need to do.
Great, thank you. I'm not seeing any other hands, so thank you again for the nice talk. The next speaker is Maylee Sanchez talking about Annie. So Maylee, you can go ahead and share your screen.
Yes, can you hear me?
Yep, I hear you. And I see your screen.
All right, and let me make this big.
Okay,
can you see that okay?
Yep, full screen now. So go ahead when you're ready.
All right, perfect. So thank you for inviting me. I'm here to talk to you about the progress we made with the Annie experiment. And so Annie is a neutrino experiment that we've deployed on the Fermilab booster neutrino beam, the same as in the short baseline program that you probably saw in talks yesterday. And it is aimed at better understanding neutrino nucleus interactions, and specifically the neutron yield from these interactions. We are also an R&D platform that will develop and demonstrate new neutrino detection technologies and techniques, in particular fast photosensors and different detection media, as I'll talk to you a little bit later about. We're a small but international collaboration, and you can see us here just before we couldn't meet in person anymore. That's literally like the weekend before. But what I'd like to tell you about is that we have built this detector. We filled it with gadolinium-loaded water since December 2019. We have all of these major systems in operation, undergoing a commissioning and calibration phase, and the fast photosensors are being prepared to be deployed. And we can show you first neutrinos and calibration data in this talk, and then expect to have physics quality data taking in the late fall this year. So the main physics of Annie is to measure the multiplicity of final state neutrons as a function of outgoing lepton momentum and direction. And as you know, neutrons are a major component of the nuclear recoil system, and as it turns out, a source of missing energy in neutrino reconstruction and detection, which then ends up being a significant systematic uncertainty, for instance, for long baseline neutrino experiments. So this is a poorly known process that needs certainly a direct measurement. So in order to carry out this measurement, I'm going to use water-loaded, gadolinium-loaded water, where the neutrons will capture, because the gadolinium gives you enhanced cross-section, say, for instance, over hydrogen captures. And we'll have a high flux of neutrinos provided by the booster beam. Other features that we expect to use is the fact that we are in the same beam as the short baseline program. In fact, just behind the SBND, the near detector of the short baseline program, which is a liquid argon detector, and it provides an opportunity of doing combined water and argon cross-section analysis on the same flux, and being able to then do measurements that allows you to relate what is essentially the two big programs in neutrino oscillation physics in the world. It also allows you the measurement allows you the potential to model the atmospheric neutrino background for a number of interesting searches that are going to be pursued by Super Kamiokande now that it has just recently loaded with gadolinium to pursue very interesting physics. So, and some of the key point is that we will analyze the high statistic sample that is relevant to a number of different measurements that are ongoing in neutrino physics. So here's the ANI detector. It's a 26-ton 26-ton steel tank loaded with gadolinium loaded water. We have 132 photomultipliers from a variety of origins. We have also 5 of these fast photosensors that I'll talk about later that adds 300 readout channels. And we have a muon range detector that has alternating layers with 2-inch iron absorber in between the muon paddles. So that's the ANI detector. A neutrino interaction in ANI then looks like you will have a neutrino charge current interaction in the fiducial volume. Here where the vertex reconstruction will be given by the fast photosensors, and then the muon with momentum will be reconstructed by the muon range detector. After the interaction, you will then have neutrons traveling and scattering until they thermalize. Once they thermalize, they will generate the key signatures, just these 8-MeV gammas, which produce the flashes of light that then are detected by the PMTs. We've done something like this before. So we did an engineering run in 2016, 2017 in a partially instrumented version of the detector. You can see it here with just the bottom PMTs instrumented. And as it happens, your most important background is in-time neutrons with the beam that are coming from neutrino interactions, either in the rock behind the detector or in the from the beam dome, and producing them, sort of scattering them through the air in what is known as skyshine. And you can see from our data here that the water essentially mitigates these neutrons as you go down. This is a vertical scan in the blue. As you go down into the detector, you see less and less of these neutrons. And if you go forward again from the detector, from the wall of the detector, then you see again less. So the water buffer allows you to mitigate the neutrons from coming from the beam. We have done the installation over the past year. You can see our detectors are going through the Fermilab site into the ANI hole, which is the old Saigon hole for those who are familiar with the site or that experiment. And we have developed a small purification system that allows us to not filter out the gadolinium while keeping the water transparency, which has also recently been published in GIST. So we've been gadolinium loaded since December 24th. And we have run a calibration campaign using LEDs that, for one thing, it tracks the transparency of the detector. You can see here a number of photoelectrons per pulse as a function. We did sort of a slow loading of the gadolinium. And you can see how that transparency has been maintained throughout. We also ran calibration with an AMBI source for sort of neutron calibration, and you can see in this plot here, the green is the neutrons when we have the source, and just the background when we have no source is a very small down here. You can also see that the neutrons, the candidates, the number of neutrons follow what you would expect in time once you do a fit to that. So we have excellent water transparency, and we demonstrated that we can see neutrons. We have also seen neutrinos. So we are reading out a 70 to 80 microsecond windows with the PMT system, which results in over 90% neutron capture efficiency. And so in these long readout window, you can see the clearly 1.6 microsecond time, which is what we expect from the beam spill. And you can see it zoomed here, sort of a close look at that. So we're observing neutrinos from the beam, and then you would expect, right, the neutrons to show up here once we're doing the measurement. We will have parallel data streams for the LAPPDs and the muon range detector, which we combine later with GPS tagging. So here's sort of first neutrino beam candidate event from back in late January. We can see PMT hits close on time. That's that tiny graph here. Those are all of the PMT hits very closely closer in time. You can see the Cherenkov disk. This is an outgoing muon in the Annie tank. And you can see no veto activity, so it's not something coming from the rock, as well as the clear long track in the muon range detector. So that's sort of one neutrino beam candidate. And then last, talk about the LAPPDs themselves. So these are these large area picosecond photo detectors that have been developed for a while now. They're 20 by 20 centimeter tiles based on microchannel plates. They have a resistive and emissive coating and microstrip anode readout. And they have fast photo detector capabilities, a 60 picosecond time resolution and an excellent position resolution. That will give us substantial benefits in terms of or reconstruction. The ANI has obtained 5 of these LAPPDs, in fact, shown here, and we're characterizing them at a facility at Fermilab to be deployed later in the summer. In fact, I can show you what the performance is for some of these tiles. This is the time resolution from our own data, our own characterization, and they fill the specs also in terms of things like after pulsing and uniformity. You can see the QE is very uniform for these tile, which are sort of early production tiles from Income, the company that produces them. So then in the last few minutes, I'll just talk a little bit about the future of ANI. I said we're a platform for detector R&D. We also plan to add water-based liquid scintillator, which is this detection medium in which the liquid scintillator droplets are dissolved in water. And it promises to combine the best of both worlds. We can have the directionality and kinematic reconstruction from the Cherenkov light and the colorimetric reconstruction from the scintillation light, while still maintaining high transparency, low cost. And combining these with fast photo sensors, it would be possible to separate, Cherenkov from scintillation light. So we have a plan of putting in a 500 liter of this liquid into ANI in a vessel for over the next year. So we see ANI as a first step in a series of efforts that will develop a series of detectors that offer new capabilities. For instance, Watchman is one, a detector for sort of non-proliferation purposes, or TEA eventually as a fourth model of opportunity in the DOOM program. So here we're testing the small sort of the technologies that might eventually be used in detectors like this. So I'll close. I think my time has run out. So I'll close with telling you and reminding you that we have now demonstrated we can observe both neutrons and neutrinos. We have an LAPPD deployment coming up in the summer, and we'll be ready for physics data taking this fall. Thank you.
Thank you. Do we have questions for Meili? You can raise your hands. Not seeing any. I should probably know this. How good is the energy reconstruction in ANI?
Well, so we don't have quite the numbers yet. I mean, we've been very busy doing all of the installation and the characterization of the LAPPDs. So I don't have a number for you, Elizabeth, but we will show those soon.
Okay, I'll be patient. Thank you. Last chance for questions. All right, I don't see any hands, so thanks, Mealy. Our next speaker is Rory Fitzpatrick, talking about the first NUE cross-section on argon measurement at ArgoNewt. And I already see your slides, very good.
Great, and you can hear me?
I can hear you just fine, and
okay.
Yes, you've just gone full screen, so go ahead when you're ready.
All right. I'm going to be talking today about ArgoNewt's most recent measurement, an electron neutrino cross-section on argon. This happens to be the first measurement of this kind on argon. ArgoNewt was a very small LRP-TPC that was deployed at Fermilab and took data about 10 years ago now. It sat underground directly in front of the MINOS near detector and received neutrinos from the NUMI beamline. Most of the data was taken in low energy anti-neutrino mode. And in that data set, we expect to see about 100 NUE charged current interactions. And I want to note that throughout this presentation, when I say NUE or electron neutrino, I'm referring both to NUEs and NUE bars because ArgoNewt can't distinguish between the two, and so we combine them. The other thing to take note of is the flux that ArgoNewt observed. The neutrino energies peak in the few GeV region, which is an interesting energy region and happens to be the region of energies that is most relevant for Dune. In studying electron neutrinos in LAR-TBCs, traditionally we use two handles to separate signal electrons from backgrounds, typically gammas, from neutral pion decay. First, we expect that electrons are generated at the neutrino interaction vertex, whereas we expect a gap between the neutrino interaction vertex and the start of the gamma shower. And second, we expect DDX at the start of the electron shower to be about 2 MeV per centimeter, whereas we expect it to be about 4 MeV per centimeter for photons. And so you can use both topology and calorimetry to differentiate between electrons and gammas in LAR-TBC, but this quickly becomes complicated at higher energies, where DIS interactions are prominent and you expect quite a lot of activity around the neutrino interaction vertex, which can overlap the vertex related information that you need in order to make this distinction. So we have to start thinking about the showers more holistically in order to make this determination. Some other things to consider when studying data in ArgoNewt is first the statistics. ArgoNewt only ran for about 5 months. As I said, there's only 100 events we expect to see in this detector from the start. So there's a limit to what can be done to inform interaction models, but there's much that can be used to inform both reconstruction and selection techniques in studying this data. ArgoNewt was also a very small detector, so we can't use a fiducial volume cut to move sufficiently far away from the edges of the detector to remove external EM-like backgrounds. And you'll see in future slides that this becomes sort of the most mitigating factor for making this selection in ArgoNewt. And then finally, an advantage that ArgoNewt has is it sat directly in front of the MINOS near detector. And so we can use MINOS data to reject charge current muon neutrino interactions in trying to select electron neutrino interactions, because the muons produced typically enter the MINOS detector and can be tagged very easily. So I'm going to touch briefly on reconstruction and some of the pre-selections we do before getting into the details of the selection itself. First, we designed custom shower reconstruction tools for this analysis, and in particular, it was designed to reconstruct only the leading, maximize the efficiency for reconstructing electrons. Second, as I mentioned, we use MINOS to reject mu charged current interactions by projecting tracks reconstructed in MINOS backwards and checking if they crossed the ArgoNewt detector. If they did, we rejected that event. And then finally, there are some basic quality cuts that remove additional through-going muons, which are produced upstream of the detector that were missed by the MINOS filter, and then some other common reconstruction failures that are sort of easy to reject outright. The one thing that I think is most interesting about the shower reconstruction itself is you can see that for quasi-elastic-like events, the reconstructed DDX at the vertex of the shower is nicely peaked around 2, where we expect it to be. But as you move towards more complicated event topologies and get into the realm of deep inelastic scattering events, you see this long tail up to higher measurements of DDX, which means we can't just rely on this handle to identify electron neutrinos in ArgoNewt, because a lot of the DIS interactions have higher than expected vertex DDX. So in order to characterize the full topology of the shower, we design a set of selection variables that are intended to characterize both the longitudinal development of the shower, starting at the vertex and moving towards the end of the shower, as well as the transverse development of the shower, because we know what electromagnetic showers look like in large DPCs. When relevant, though, we have to charge normalize these variables because Argonaute is a small detector and we can't rely on containment to select events. And so nearly all of our events exit the detector, meaning we can't reconstruct energy in a straightforward way. So all of these variables that we design are charge normalized in order to get around the fact that we don't see the full shower. After defining that set of variables, we use them to train a BDT that's intended to identify signal based on the reconstructed shower topology. And this BDT serves two purposes. It distinguishes well-reconstructed signal from well-reconstructed background. But the second purpose is to reject reconstruction failures. And that's because in designing the shower reconstruction, we had the goal of reconstructing as many electron neutrino showers as possible, knowing that further down the line in this selection, we could reject things that had been reconstructed in error based on their topology. And you can also see that in the distribution of this BDT, the external background, this brown distribution, tends to contributes the most to our background before the BDT selection. But these tend to be typically reconstructed, and they also tend to look extremely background-like. And so they pile up at lower BDT scores. The other thing I'll say, I had mentioned that the gap between the neutrino vertex and the start of the shower vertex is typically used in analyses like these. In Argonaute, with the high neutrino energies that typically result in large track multiplicities, and the fact that we can't see the full event typically because it exits the detector, this all complicates automated reconstruction of the gap, yielding very weak separation power, and so we don't use it at all in this analysis. So because the external background contributes most significantly here, I want to spend a little bit of time talking about it. Originally, we observed a deficit in simulation relative to data of this external background. I show a couple examples in data on the left. You can see these are quite obviously events that are generated outside of the detector, but produce some kind of EM-like activity inside of the detector. And we see this deficit because Argonaute simulation only includes neutrino interactions that happen inside of the cryostat, not ones that happen external to the cryostat. There's an additional time dependence, which would make this hard to model because Minerva was actively being installed in the same cavern during the Argonaute data taking. And so we developed an approach for handling this external background. First, we wanted to understand and correct for this deficit that we observe, and then validate that correction, which is a scale factor as a function of BDT score using a hand scan of in a back-only sideband to confirm that the expected external background number matches what we observe in data after our correction. But in order to mitigate uncertainties associated with the scale factor, we also pick a very stringent signal selection with very high purity, which essentially removes all impact this external background has on the selection. And then we additionally assign a very conservative uncertainty, which encompasses the multiple correction methods that were tested in trying to understand this external background. So we understand it, but we've also moved its impact for the final result. So with all that in mind, we define our signal selection to be interactions that have a BDT score above 0.9, which gives us 13 events in data. Of those 13 events, we expect about 11.2 to be signal and about 3 of them to be background interactions. This yields just over 10% efficiency with almost 80% purity. And you can see that the reconstructed DEDX of the signal-like events are here, peak nicely around 2, with good agreement between data and Monte Carlo, given the statistics. And one example of one of the selected interactions is shown on the right. It was nice to see that this selected event matched a selected event that was picked in a previous Argonaute analysis that relied on hand scanning. The nice thing about having so few events is the fact that we can show you all of them. So these are all 13 events that were selected in this analysis. And I'll get more into the topologies of these events in a future slide. But you can see they do generally agree with our expectation of the topologies given the selection we've defined. And we do see sort of down here the 3 obvious backgrounds. We can also extract a cross-section with these 13 events, which agrees with Gini. And then because we know that the angular resolution of the reconstruction is very high, we also extracted a differential cross-section in terms of electron-neutrino angle with respect to the nu-me beamline, which again agrees with simulation given the high statistical errors on this analysis, which dominate our systematic errors. It's also worth noting these cross-sections are defined to be combined nu-e plus nu-e bar cross-sections because, as I said, we can't distinguish between the two. I'll also note that the dominant systematic uncertainties, or they are extremely subdominant to the statistical uncertainties, are the hadron formation zone used in Gini, which is relevant to the multiplicity near the electron or the neutrino interaction vertex, and also the quantity of the external background, though it is still, as I said, subdominant to any statistical uncertainty we have here. And to give you a sense, these are the neutrino beam energies we're working with. And so finally, I want to talk a little bit about the signal topologies. As I showed you, the topologies for the events we selected tend to be simpler topologies. And if you look at a sample of simulated electron neutrinos, you can see that the selection at 0.9 is extremely efficient for quasi-elastic-like interactions and tends to be less efficient for deep and elastic scattering interactions. This isn't surprising. We were sort of forced to this very stringent selection because of the external background, but we can assume that future detectors won't have this issue because they'll be able to move further away from the detector walls. We did, however, do a subsequent hand scan of a looser selection for BDT score above 0.7, which remained consistent with the expectation of topologies in the sample, and also yielded a larger sample of very clear high multiplicity deep and elastic scattering interactions that were selected using this method. And I've shown 2 examples here. You can see this one's a nice electron neutrino event that also includes a pi knot. And all that said, there are also these cases where deep and elastic scattering signal and background events are simply impossible to distinguish because you have so much activity coming out of the vertex. And so there's a certain ceiling you reach with trying to reconstruct these complex topologies. And so finally, I'll just end to say that this is the first end-to-end automated reconstruction and selection of electron neutrinos from neutrino beam data on argon. And it's particularly interesting because it's GeV scale neutrino beam data. And it provides unique insight into the challenges of working with this energy data. And it's also important to keep developing techniques like this to cross-check the machine learning-based techniques that are currently being developed too. So thank you.
Thank you. Do we have questions? You can raise your hands in the Zoom. All right, I have one. So you have a fairly low selection efficiency. Do you have a sense of how much of that comes from having to deal with this external background because you can't make a fiducial volume cut? Like if everything else were equal, but you were in a bigger detector, do you know what your efficiency would be approximately?
Yeah, so it's hard to estimate because there are a couple things that are conflated. There's the external background, and there's also just the fact that we can't see the entire event because they're not contained. And so it makes it harder to start reconstructing events to begin with. So the limit in efficiency here is in part just the reconstruction efficiency itself, how many showers we actually say these look like showers. So the biggest limitation here in efficiency is the actual reconstruction itself, and future detectors will also have a benefit there. Bespoke reconstruction.
Okay, thanks. Other questions? All right, I don't see any. Thanks again. So our last speaker in this part of the session is Vincent Basque, speaking about recent progress in Lariat. So you can go ahead and share. There you are.
There you go. I assume everything is right now.
All right, I see it and I hear you. So you can go ahead whenever you are ready.
All right, perfect. Yeah, so my name is Vincent. I'll be talking about the recent progress in Lariat, and it will go quickly. It's just the last hour before the break. So funnily enough, the detector that Rory was just describing, Argonaut, this is basically what Argonaut has become after being at the NUMU beamline. So as you know, Argonaut and Lariat are very small LARC-TPCs, and I made a table just at the bottom here to just give you a sense of the dimensions and the type of collection system and wire spacing that we have in these LARC-TPCs. But the main difference and the big important thing about Lariat is that it is a test beam experiment, meaning it was at the end of a beam of known charged particles. So just in front of the Lariat TPC, there was auxiliary detectors to ID the particles and their momentum, and we use that to do particle selection. So the whole program of Lariat really combines some physics and R&D goals, and these are very important because they can provide crucial calibration information for what I call the not so future LARC-TPC, so the SBM program and Dune. And if you're curious, here's a link to the detector paper. Most of the information I'll be talking about today is in the paper. So what goes inside the TPC? Well, Lariat had 3 wire planes. The outer plane was acting like a shielding plane, and then the 2 innermost were the readout planes at different angles, obviously to make the 3D reconstruction. We had about 240 wires per plane. The nominal field was the typical 500 volt per centimeter. And if you're curious, during the various run of Lariat, there was different pitches from 4 to 5 to 3 millimeters. The two things that really makes Lariat very special at this point is that it used cold electronics versus other experiments at the time that didn't. So the cold electronics were actually attached to the TPC and inside the cryostat. And the other very big difference from Argonaut is that we have light information. There were PMTs and SIPMs and even Arapucas that were attached to the cryostat to actually detect the light that we get out of LARC-TPC events. So this is the Fermilab Accelerator Complex. And just to point out that Lariat sits or sat at the test beam facility, which is at the end of the 120 GeV proton beam here at Fermilab. But we're not looking at these proton exactly. So as this proton beam goes into the test beam facility, it interacted or hit a tungsten target, which produced a secondary beam of mainly pions that will then go towards the Lariat enclosure. But again, we're not looking at a pion beam, we're looking at this tertiary beam. So what happens is this pion beam actually encounters another target, a copper target here, and then the particles that are produced, so this whole family of electron, muon, pions, kaons, protons, and deuteriums, both in NT and non-NT particles, are produced. So these particles will go through the whole beamline auxiliary detectors and then go to the TPC. So I'm sure many of you are aware, but these test beam experiments have different components, and the main components are really these time of flight to actually know the time it took the particle from exiting the sphere collimator to just before it enters the TPC, as well as these wire chambers in red, where we can actually track the particle to especially get its trajectory, and the dipole magnets that really helps us to essentially make a mass spectrometer of the particles. And these magnets, we actually have different intensity, and both in negative and positive polarity, which actually gave us a chance to choose the sign of the particles. But now that we have these, we have this beamline auxiliary detectors. We can identify the particle species using the combination of the time of flight, the wire chamber hits, and the magnet polarity. And we can make these very nice plots that I'm sure you've seen before. That's on the bottom left, where I just plotted the time of flight versus the reconstructed beamline momentum. And you have these nice bands for the different particle types. So for example, the big band right here is really where you have the overlay of the expectation of the protons. And you see a really nice one here, and then you can see some deuterions and some kaons here, and then the rest are just accumulated down here. But now that we have these beamline particles, we can actually select them by either looking at the mass that they have with the information that we have here. But now if we want to, let's say, do a proton analysis, well, we can select these, and then we need to see where they are in the TPC. So this is when we can use this wire chamber hits, where we look at the projected track. So if you want the wire chamber projected track into the TPC, and then we can look at the tracks that mostly match the TPC tracks, that mostly match the projected track. So we can have some parameters that actually guide us to help us determine which tracks that we're actually looking for. Now that we have these particles, we know what they are, where they come from, and where they're on TPC. I can talk to you about the actual physics program of Laird. So the main physics was really look at these hadron interaction cross-section on argon. So especially the pions and kaons, but we can also perform protons. But as well, Laird also, as I mentioned before, did a lot of R&D. So the three main things that I'll try to talk to you about today is, this calibration of beam particles, because we know these particles, they're coming from the beam. And interestingly enough, the particles that Laird sees they cover the phase space that we get from accelerated neutrino interaction. So it's really important to be able to identify them. Another cool thing that we've done is really combining the scintillation light and ionization charge in analyses to see what we get out of that. And we've even performed some antiproton annihilation on argon. So the first thing I'll go over is the total cross-section. And Laird, if you want, has two firsts. It's the first measurement of total cross-section on liquid argon in this energy range, about less than 1 GeV, for both the pi minus, which is on top, and the K plus here on the bottom. So on the left side, you see it's essentially the composition of the beam with the data in black, and then the simulation, the contribution of every particle type simulated in the bands. So if we start for the pions, you have this big yellow band, and then once you select your particle in the TPC, you can actually calculate the cross section. So a few comments on this cross section. The uncertainty is really dominated by systematic. There was a lot of pions, but really the systematic is really what's dominated here, because it's really difficult to the removal of background interactions, so decay and capture. But overall, there's a good agreement with Gian for prediction, and there's final cross-check ongoing with pi plus analysis that is also progressing in parallel. And then we can do the same thing with kaons. There's significantly much less kaons. So there's about 1,000 TPC event that were selected here. So obviously the statistical error dominates over. There is some tension with the kaons interaction mode, but this measurement can actually help in its tuning. So two very important measurements. As I quickly mentioned before, the antiprotons are also made in the beamline. It's a very small amount of them, and you can't even see it here. But we've seen there's about 100 antiproton candidates that have been found annihilating at flight or rest inside the TPC. So why do we want to look at these antiproton events? Is their annihilation can help the neutron anti-neutron oscillation searches, because the topology of the event is very similar. So this is the star shape that you can actually see in one of the events, the star shape event that you have. And the outgoing energy of these particles is about the same for both the neutron oscillation and the proton and antiproton annihilation, which is about twice the mass of the proton. So the goal of this analysis is to look at or to measure the Algorian species, energy, and direction. So here I have two of my personal favorite events, which you can clearly see that something that would be like an antiproton candidate that comes in, annihilates, and then creates these very nice star-shaped pattern. The other thing that Laird has done is try to improve the collection efficiency. The scintillation light that gets produced in large TPC is it's a low wavelength. It's 128 nanometers. And this is not, most conventional light sensors cannot actually see this light, or are blind to this light. So typical ways is to cover the light sensors with some wavelength shifter. And here I have a nice example of a PMT covered with some wavelength shifter. So in this case, it was TPB, and how it glows into the visible range, which can actually be seen by a PMT. So instead of coding light sensors, Laird has decided to cover the whole field cage of the detector of the TPC of a TPB coated on reflector foils. So the cartoon here, if you want, elaborates on how it works. You have your VUV photon that comes in, interacts or gets absorbed by the TPB. And then if this is re-emitted in the opposite direction of where you want it to go, it will continue, but then it will hit this reflector and bounce back. And then we can actually recover the light that you would normally lose. So here, what I've shown is a simulation of the amount of light that we expect, so the light yield. So on the left, we have, if you only coat the actual light sensor, you have a very big spot of where you expect your photon to be. That's totally what's expected. But if you code the actual field cage, you have a very nice, more uniform and high light yield across the whole detector, which is very nice too. That could enable measurements such as this one. So what can we do with all this light? So what we have done essentially, if you want to prove a concept, by looking at cosmic Michel electrons. So these are low energy electron emitted by stopping muon inside the detector. And we dedicated some scintillation light trigger to be able to catch them. And what we have shown is if we do analysis only looking at the charge information, or if we also add, or if we combine the light information to this charge information, we see that we recover, if you look at the truth information, which is this dotted line on both graphs, you see that we recover a lot of it, especially at the tails where we recover what we would normally lose. So we really mitigate these low energy tails, and all of the information that we lose is partially recovered. Here, there's a very nice paper if you want to read more information on how this analysis was performed. So layer may be small in size, one of the smallest, but as you could, I hope I convinced you that it is clearly rich in physics. We have used the Fermilab test beam facility, and we have performed measurements of the total cross-section on pions, pi minus and k pluses at this 1 GeV range. We've shown the powerful, or how powerful having more light in a large TPC can do, and what it can do for energy reconstruction. And another thing that we are currently working on is looking at what we can do out of these 100 candidates of anti-proton annihilation. And all of this information is really important for the short baseline neutrino program at Fermilab, and obviously Dune. And please stay tuned as more of these results are currently pipelined.
Thank you. Questions for Vincent? I see one. Go ahead, Wencheng. I think you can unmute yourself.
This is Wenqing. So the idea of coding the entire detector case is really interesting. Yeah. Is there any loss of night? Seems that there isn't. I don't quite understand this actually.
If there was what, sorry?
Night loss, not, for example, some absorption in the TPB.
Light noise. Interesting. I'm not sure. I guess. So what you could, I mean, the whole process of changing or wavelength shifting the light is very fast. And if you think of a larger scale, you could think that some of the visible light would take longer maybe, but it actually it actually goes quicker in liquid argon. There's less Rayleigh scattering for the visible light. So maybe at long distance, you recover a lot of the light that you lose, but actually to translate that into noise, I'm not actually sure.
Okay, and the plots on the right actually show that you don't, I mean, you actually paid for doing this.
Yeah.
Right? Okay.
Yeah, exactly. Yeah. You see that you don't have a spot, so your light sensors are in the same places, except now your photon really needs to go there to actually be detected. While here it can go all around, and the visible light is what you actually measure. You don't really measure the VUV at this point. You measure the wavelength shifted light if you do it this way.
Okay, thank you.
Any more questions? Last chance. All right, well, that ends this part of the session. Thank you to all of the speakers for the very interesting talks and for being so good about being on time. You made my job very easy. So I appreciate that. So in the schedule now, we have until 1:30 for a break. And when we come back, Vit will be in charge. So I will say goodbye. Do you have any announcements, Vit, before we go away?
Yes, I would like to, first of all, can you hear me?
Yes.
I would like to encourage people who didn't ask questions during the session that you can discuss things at the matter most. This is one thing. Second is I would like to encourage speakers of the second half of today's session to test their audio, video during the break. That's all.
Thank you, Vit. This is Wenqing. I have a quick question. Will you also use this digital reminder, like has been used?
Why do we use what?
A digital display on the slide with 2 minutes and 1 minute, 1 minute reminder. Will you continue to use that? So the speakers in the first session has this reminder display on their slides 2 minutes before the end of the talk.
Yeah.
Are we still going to use that?
Yes.
Okay, good. That's very useful, I think.
I agree. So, good afternoon. Let's start the second half of the today's session. And the first speaker is Laura Bernard, who will talk about spallation background in the Super Kamiokande experiment. So Laura, please can you share your screen?
Yes.
Fine, so let's start. You have 12 minutes.
Okay. So hello, my name is Laura Bernard, and I will be speaking on behalf of the Super Kamiokande collaboration on the spallation background in this experiment. So the Super Kamiokande experiment has played a major role in astrophysics by investigating low energy neutrinos, and notably it has been instrumental in the characterization of the boron 8 solar neutrino spectrum. And also it currently exhibits the best sensitivity to relic neutrinos from distant supernova, and there will be a talk on this tomorrow by Sonia El-Hidri. So while solar neutrinos are detected through their elastic scattering of electronic neutrinos, we use the electronic anti-neutrino flux from the supernova relic and detect them through the inverse beta decay. We expect very few events, 5 to 20 events per year. This is a very weak signal. So the advantage of using this IBD interaction is that we have a time and space correlated signal. You can see it on the scheme here with a prompt signal and also a delayed signal coming from the capture of the neutron on the hydrogen in water. So this is a very weak signal. It's 2.2 NV gamma. But this helps reducing the background. And if you look at the right plot, so the signal and backgrounds for supernova relic antineutrinos, you can see that there is a kind of golden region here where the neutrino from supernova seem to be reachable. The main neutrino-induced backgrounds are reactor antineutrinos and atmospheric antineutrinos. However, in this golden region, there is actually a background that is very dominant, and it comes from muon spallation in water. This is also dominant in the solar researches. So this background is well characterized in liquid scintillators, but not yet in water detectors. And this is why we need simulation, and this is what this talk is about. So this is the Super Kamiokande detector. It's a water Cherenkov detector located in the Kamioka mine in Japan. It's 1,000 meters underground, and at this depth we have around 2 muons per second. It's composed of an outer detector, inner detector, and the fiducial volume is 22 kilotons. So the PMTs are used to read the lights from the Cherenkov effect. Now we are in phase 6. Sorry, can you hear better? Okay, I think I forgot to put this. So now we are in the phase 6, and an important point is that our Japanese collaborators have just started loading the water with some gadolinium that is dissolved in the water, and this will greatly improve the neutron tagging. As you can see here from the IBD, for example, the neutron will be captured on gadolinium, and this is an 8 MeV gamma cascade, so which is much easier to see. So this will greatly reduce the spallation background. Here we can see an illustration of the muon-induced spallation in the Super Kamiokande water tank. What happens is that muons produce daughter particles that initiate electromagnetic and hadronic showers through successive spallation processes. And today we know that hadronic showers are the dominant process in the production of unstable isotopes. You can see the isotopes here in red. And the decays of these isotopes, so mainly electrons, positrons, gammas, or neutrons, or a background at low energy, so below 20 MeV. A good point is that the shower and isotopes can be located by the neutron captures that come from the neutron from the hadronic shower in the medium. So how do we deal with spallation in the data? The information has been extracted directly from the data. So we looked for correlation between low energy events, so the isotope candidates, and the muon track, such as transverse distance and longitudinal distance to the maximum of deposited energy of the muon. And more recently, there is also the neutron cloud that is used to locate the hadronic shower. And for that, there's a trigger system that is used called WIT, and it allows for a lower threshold to see the 2.2 MeV gammas from the neutron capture on hydrogens. So although the spallation background is eliminated at about 90%, we still need to reduce even more this background. So this is the point of the simulations. So we start our simulations from simulating the muon flux at the super Kamiokande level. And for that, we use MUSIC, which is a 3D Monte Carlo code for muon propagation through the rock, developed a long time ago. I'm sorry, in 1997. And to reach the super Kamiokande tank, a muon must have an energy that is greater than 1.3 TeV. And the mean energy of the muons reaching SK is 258 GeV, but the spectrum is quite wide and it can extend up to several TeV. So once we have this muon flux at the super K entrance, we used FLUCA, which is a fully integrated particle physics Monte Carlo simulation package. It's good to know that a first FLUCA-based simulation of vertical muons in the water tank was already done in 2014. So what we did is that we reproduced this simulation and we improved it, adapted it better by using the real MUSIC flux and also adding the mu plus component of the flux. And this actually reduces the isotope yields, mainly the nitrogen-16. And most importantly, we interfaced FLUCA with the official simulation of Super K. So you can see here a comparison of the isotope production. Red is the data for the different isotopes produced, and you can compare to the green dot, that is our simulation. The comparison is within a factor of a few, which is consistent with uncertainties from nuclear physics models. We also developed very recently a Giant-4-based simulation of spallation, and we compared it to FLUCA. We are quite happy with it because the overall observables are very well reproduced. You can see here the path length of all the particles in the shower, and also here the distance to the muon track of the particles, left for Giant and right for FLUCA. And we also checked the yield of the dominant isotopes, and they are within a factor of 4. However, there is a bit of a discrepancy for lithium-8, which is the third most important isotope. But anyway, these simulations are about to be implemented in a Giant-4 super Kamiokande simulation, which is called WCSIM. And this will allow better understanding of the reconstruction, and also could be of interest for the hyper-K studies since it's already coded in WCSIM. So we chose to use the FLUCA simulation to interface it with the official Super K detector simulation, which is called SK-DATESIM and which is Giant-3 based. So we really needed to evaluate how to propagate the FLUCA events to SK-DATESIM without repeating interactions. So since the unstable isotopes are mainly produced in the hadronic showers, we saved this information from FLUCA, so pions, neutrons, gammas up to the isotope decays, and we input this in the SK-DATESIM, where we turned off the creation of secondaries in the hadronic processes and also the muon-nuclear interactions. And for the electromagnetic part, we let SK-DATESIM take care of it. So you can see here an example of simulated event with the generated muon track, reconstructed muon track after applying the reconstruction filters. In green, the neutron cloud, and red, some isotopes. Of course, the tricky part is the muon and shower energy deposition and reconstruction. So going to the comparison of data with Monte Carlo, this is actually the first comparison that is done for spallation background in water. We used the supernova relic analysis of May 2020. And you can see here the muon directions in the entry of the detector, so X, Y, and Z. This validates the music simulation, although we have some discrepancies that are still under study for the track length of the muon. Here, if we look at the energy deposition of the muon, we have several observables like the total deposited charge, the residual charge, so the total minus the minimum ionizing part, also the charge in the higher segments and the location of this higher segment. These results are actually quite good and validate. They are on the way of validating the Fluka shower model and interfacing with SKDate sim. Now, if we look at the isotope candidates, so the main observables are the transverse distance to the track here in blue. This is a very nice agreement. However, for the longitudinal distance from the isotope to the maximum of deposited charge, so in orange here, we have a wider distribution than in the data. So we need to investigate potential misreconstructions of this maximum of the EDX. And finally, the neutron cloud is, so the neutrons are very abundant, so they can be used to locate the shower. And here you can see also observables like transverse distance of neutrons to the muon track, which is a really good. And we have this longitudinal distance of the neutrons to the muon entry point, which is slightly different, like in the case of the isotopes. So these studies are still under progress, but it is very promising. And most of all, with the recent dissolving of the gadolinium in the water, we expect to have a very much better tagging of the neutron captures. And since I have 10 seconds left, I will speak a bit about gadolinium. So these are the first runs. And we officially see the neutron captures on gadolinium after showering muons. You can see here the height of the detector and the radius, and how day per day the gadolinium, so the neutron captures on gadolinium are getting upper and upper in the detector as the gadolinium is being spread. So this is promising upcoming results. And in conclusion, so muon-induced spallation is a dominant background for solar and supernova relic neutrinos. And we need simulations in water to improve rejection now. So those simulations are already in place with cross-checks between Fluka and Giant 4. And I showed you first comparisons to data. We find nice agreements for this first comparison. And of course, this is still under study. And we wait for a new analysis thanks to the gadolinium in water. Thank you for your attention.
Thank you, Laura, for a nice talk. Questions? I see one hand raised. It is Wenxu.
Yeah, hi, this is Wenqing. So very nice talk. I'm super interested in this. Fluka and the data are quite consistent, but you said Giant 4 has uncertainty about a factor of 4 on one of the dominant component. Does that mean Giant 4 is less favored by the data?
So I'm not sure I understood exactly what you said. Could you repeat? You said that you were surprised that this data is consistent with the Fluka plus Giant 3 simulation, or you were speaking about Giant 4 simulation?
Yeah, this one, this slide here.
Okay, sorry.
So this is to compare with Giant 4 with the Fluka, and the data support the Fluka. Does that imply Giant 4 is not consistent with Fluka with a factor of 4?
For the yields.
Right.
Yes, yeah. We have several factors. Like we have a factor of 4 for boron 12, and for the dominant one, which is nitrogen 16, there's a factor 2.2, something like this. But actually, it's quite consistent with the uncertainties that you get from nuclear physics models.
Okay, but does the data, would the data speak on this at all? Maybe not directly.
I'm sorry, I don't understand the word that you use.
Sorry, can you compare this with data directly? Maybe not.
So you mean doing this plot here, but with a giant?
Right.
Comparing the...
Yeah.
Okay, we haven't done this yet, but we have the numbers, but haven't done the plot yet. But so we would have, you would see here for nitrogen 16, for example, this factor of 2 difference with a giant. So it's a bit different indeed.
Okay, thank you very much.
And this is why actually we wanted to do these 2 comparisons, so these 2 simulations to really compare the yields and other.
Okay, thank you.
Thank you, Laura. I'm sorry we don't have time for other questions. So you can continue discussion on Mattermost. So the next speaker is Mark Scott, who is talking about long baseline neutrino oscillation sensitivities with hyper-Kamiokande. So Mark, please.
Hi, good morning. Can you hear me? And can you see my screen?
Yes, I do. I hear you.
Perfect. Okay, so first of all, I'd like to thank you all for letting me come here and talk about the long baseline neutrino.
If you can speak louder, it would be better.
Certainly. First of all, I'd like to thank you for inviting me to come here to talk about the long baseline neutrino oscillation sensitivities with hyper-Kamiokande. The biggest news since the last ICHEP conference is, of course, that Hyper-K has been approved. So KEK has agreed to operate and upgrade the J-Park beamline to 1.3 megawatts, and the University of Tokyo will construct and operate the Hyper-Kamiokande detector. And actually, construction has begun. You can see the work yard on the bottom right of this slide, and operation is due to begin in 2027. So Hyper-Kamiokande builds on an illustrious history of water Cherenkov detectors in Kamioka. It started with Kamiokande in the 1980s. We just heard about Super Kamiokande, which is currently taking data. And as you can see here, the size of these detectors has grown with each iteration by about a factor 8 at each step. Now, these are water Cherenkov detectors. And so they're looking for the Cherenkov light from charged particles produced by neutrino interactions. A muon neutrino will produce a charged muon, which doesn't scatter in the water. So you get a very clearly defined Cherenkov ring on the wall of your detector, as shown on the bottom left. And an electron is lighter, it scatters from the electrons in the water. And so you get a more diffuse ring appearing. And so we can use this technology to separate muons and electrons with a greater than 99% purity and have very precise momentum and direction reconstruction. So the Hyper-Kamiokande experiment, I said before, it's an increased power neutrino beam and a larger FAR detector. So in total, these give us a factor 20 increase in statistics compared to the T2K experiment. We also have a new intermediate detector planned for Hyper-Kamiokande and will inherit upgraded near detectors, which you'll hear about in the talk following this. And finally, we have improved photosensors, which double the quantum efficiency compared to Super K. And so you can see there's talks listed here later in the conference discussing these developments. Okay, so this is the first neutrino oscillation talk of this session today. As you can see on the top right, I've written out the oscillation probability for neutrinos. And this probability of a alpha type neutrino oscillating to a beta type depends on these mixing matrix U, the mass squared of the neutrino, and the distance and energy that it's traveled. And so in these long baseline experiments, we're measuring the flavor composition of our neutrino beams as a function of L over E to extract these mixing parameters. Something that's unique to the next generation of long baseline experiments is that they're really going to have the statistics to test CP symmetry directly by comparing neutrino beams to antineutrino beams. And so if we see a difference in the measured oscillation probability, as you can see on the bottom here, then that would be direct evidence for CP violation in the neutrino sector. Okay, so a quick word on formalism. We're following the standard PM&S description of neutrino oscillations. So we have three mixing angles, theta 2,3, theta 1,3, and theta 1,2. We have three neutrino mass states, giving us two mass splittings, delta m squared 1, 2, delta m squared 2, 3, and a single CP violating phase, delta CP. Now, there are three main questions that we want to answer in neutrino physics. The first is whether theta 2,3 is above or below 45 degrees. This is referred to as the octant theta 2,3. The second, we want to know the neutrino mass ordering, whether the M3 neutrino mass state is heavier or lighter than the M1 and M2 states. And this, you have either normal or inverted ordering. And then finally, the big question, of course, is whether neutrinos violate CP symmetry. So these are the questions we want to answer with Hypercamiocande. So as I said, this is a much larger experiment than T2K, and so we have much greater statistical power. I'm showing here the expected number of events in our electron neutrino sample for the neutrino beam mode on the left and the antineutrino beam mode on the right. We've taken these, estimated these, by scaling the existing super Camiocande Monte Carlo to the hyper K fiducial volume and exposure. So this includes the full likelihood-based Fit-Kuhn reconstruction that has been so powerful at super K. Having done this, we end up with about 2,300 electron neutrino events and just under 2,000 electron antineutrino events, assuming sine delta CP is 0, so CP is conserved. We can then compare this event rate to what we see in the detector for different values of delta CP, shown on the bottom. And for example, in blue here, if delta CP is minus pi by 2, you see that your electron neutrino sample is increased relative to delta CP equals 0, and your antineutrino electron-like sample is decreased. And so it's by comparing the relative rates of these two samples that we have sensitivity to delta CP. Alongside the electron neutrino samples, we also have a very large selection of muon neutrinos, approximately 10,000 in neutrino mode and 12,000 in antineutrino mode. Okay, so this talk is focusing mainly on the oscillation analysis of hyper K, and this follows the T2K analysis method. So we have a parameterized flux model and a parameterized interaction cross-section model. These are then tuned and constrained by a suite of near detectors, and the result of that is passed on to our far detector simulation, where we use simulated events to produce constraints on our oscillation parameters. Now, I've made a case for the large statistics at hyper K, and because of this, I'm going to have a particular focus on the systematics that we assume in these sensitivity studies. So to start, for the neutrino flux on the left, we take the Na61 SHINE thin target hadron production data and its associated uncertainties to provide the hadron production uncertainties in our flux. We also take the J-Park neutrino beamline measurements to give us additional uncertainties on the focusing of the beam. For the neutrino cross-section, this is based on the Newt 5.4 model and the T2K 2018 uncertainty model as our baseline. It's described in the paper here. One significant change with respect to that model is that the T2K model has a heuristic nucleon removal energy uncertainty, whereas for hyper K, we've just included this directly as an energy scale uncertainty at hyper K itself We then take the T2K near detector fit, which constrains these models to the near detector data at T2K as our initial starting point for what we expect the hyper-K near detectors to be able to do. Once we have this, we scale the uncertainties accounting for the extra exposure at hyper-K, but also the improved near detector performance, which Mark Hartz will talk about in the talk following this. Okay, so putting all of this together, all of the analyses I'm showing here assume 10 years of hyper-K data. We have a 1:3 ratio of neutrino beam to antineutrino beam, and unless it's stated otherwise, this is not including the atmospheric neutrino sample. The plot here shows our sensitivity to exclude the wrong sine squared theta 2,3 octant as a function of true value of sine squared theta 2,3. The blue dashed curve is assuming the T2K 2018 systematic uncertainties, and then the dashed red is the improved systematics that I just spoke about, whilst black is the statistics only measurement. And to put some numbers on this, the uncertainty on the muon neutrino rate from the T2K analysis is about 4.6%, whereas the improved hyper-K systematics, we estimate this to be just under 2%. So we're really reducing those quite significantly and improving our exclusion values of the wrong octant. So with this analysis, we could achieve a 3 sigma exclusion for sine squared theta 2,3 below 0.47 and above 0.55. Moving on to the CP violation sensitivity. The plot here shows our ability to exclude CP conservation versus the true value of delta CP. Again, the blue curve is for the T2K 2018 systematics model. The dashed red is our improved model, and black is statistics only. Now, you can see the black curve here shows a real power to exclude CP conservation due to the high statistics of hyper-K, but the systematics have a considerable effect. You're dropping from about 11 sigma down to just over 6 sigma with the T2K systematic uncertainty model. And putting this together with our improved systematics, we expect to exclude roughly 60% of the true values of delta CP at 5 sigma after 10 years data taking at hyper-K. You can look at this over time. So the plot again is showing the percentage of true values of delta CP for which CP conservation can be excluded as a function of running year of hyper-K. And the gray area is a 3 sigma exclusion, the red is a 5 sigma exclusion. And the only thing to point out here is that we can really achieve a quite significant result, a 3 sigma CP violation measurement over about 50% of the allowed values of delta CP after only 2 years of operation. So even with a relatively short, small data set, we can do some really interesting physics measurements. Finally, another quick word about CP violation and the systematic uncertainties. So the plot here shows our sensitivity to exclude CP conservation, but each curve now uses the improved systematics for hyper-K. The only difference is our assumption of the nu-E over nu-E bar cross-section uncertainty, going from 3.6% in purple up to 2% in blue, 1% in red, and then 0 for statistics only. And just to give you a ballpark figure, the current theory uncertainty is 3.2%. So it's just better than this dashed purple line here. So clearly, if we want to really get all of the benefit from the next generation of long baseline experiments, we have to measure this nu-E over nu-E bar cross-section uncertainty as well as we possibly can. All right, so the final study I want to show is the effect of adding atmospheric neutrinos. As you know, these have longer baseline and higher energy than the beam neutrinos at hyper-K, so give us some sensitivity to the neutrino mass ordering. This is the same CP sensitivity plot again as we've seen before, but this time we assume that the mass ordering is unknown. And in this situation, the beam analysis only, shown in red, you can see there are some regions of delta CP where we have a reduced sensitivity. If you add the atmospheric neutrinos to this, this sensitivity improves dramatically, And we can actually exclude these regions of delta CP at 5 sigma again, whereas the beam only, we were not able to do so. And if you look at the significance of excluding the incorrect mass ordering by itself, Hyper-K can achieve a 4 to 6 sigma exclusion, depending on the true value of sine squared theta 2, 3. Okay, so thank you very much. I've presented updated Hyper-K long baseline oscillation parameter sensitivities here and what we can do after 10 years of data taking. The final plot here just shows our ability to exclude CP conservation, assuming delta CP is minus pi by 2 or CP is maximally violated. So you can really see that Hyper-K is a order of magnitude better than the existing T2K and even the T2K2 experiments. And yes, if anyone's interested in the astrophysical sensitivities of Hyper-K, Jano-san is giving a talk tomorrow at 10:30. Thank you very much.
Thank you, Mark, for interesting talk. Unfortunately, we are rather late, so I would prefer to continue with the next talk. And this is another Mark Hartz. We'll talk about new detectors for Hyper-K.
Yep, can you hear me?
Yes.
Okay, and you can see my slides?
Yes, I can.
Okay, right, so yeah, thank you for this opportunity to talk about our new detectors for Hyper-K. So I think Mark already described well in the previous talk what the Hyper-K experiment is. We have a new, very large detector with 187 kiloton fiducial mass in the Hyper-K detector, and also upgrades to the beam to get higher beam power. And as I'll talk about in this talk, upgrades and new near detectors to help us control systematic uncertainties for the experiment. So Mark already talked about how we have very large samples of electron neutrino or anti-neutrino candidates that are used in the CP violation measurement, about 2,000 candidate events of each that allow us to see the CP asymmetry potentially very clearly if it's a significant CP effect in the neutrino oscillations. But of course, with this very large statistics, there's a lot of statistical power in the data that will be collected. So we really have to control systematic uncertainties. So we're talking about a 3% error on the CP violation measurement, statistical uncertainty, and for example, T2K's published uncertainties are around 6% at the moment. So these uncertainties can enter in through the neutrino flux model or the neutrino cross-section model or the detector model, but we'll primarily focus on the first two since they're constrained by near detector data. So talking about the neutrino flux model or the beam systematics, we can kind of think of different categories. So one is just the uncertainties that come in the modeling of the hadron production in the target for the experiment. And of course, there are external hadron production measurements that are used to really constrain this. But there can also be, for example, uncertainties in the beam direction. When you're using an off-axis beam like Hyper-K is using, what that essentially does is shift the beam peak here. So we need measurements to constrain the beam direction. And then there's also potentially uncertainties in the wrong sign contribution of the beam. So these are the defocus. So when we're running in anti-neutrino mode, these would be, say, pi plus that are defocused, but there's still some significant contribution to the overall flux. In the case of anti-neutrino mode of the beam, the neutrinos are enhanced by the relative cross-section, so we have to care about that background. So measurements that constrain that wrong sign contribution of the beam are important. On the interaction modeling side, we're primarily looking at quasi-elastic interactions, so interactions of a single bound nucleon, and we reconstruct energy based on the kinematics of the charged lepton that we observe in the final state. In a water Cherenkov detector, typically any emitted protons are below Cherenkov threshold, so we don't see them. But there can be nuclear effects that change both the strength of the cross-section and also this energy inference. So For example, you can have this 2-nucleon process where you're essentially scattering off of a pair of correlated nucleons, and you have multiple nucleons in the final state, and the energy reconstruction for those won't be the same as quasi-elastic. So modeling those types of events that aren't quite quasi-elastic and can affect the energy inference is very important. In particular, for example, in the theta 2-3 measurement, where we're looking at an oscillation effect, and many of the events that populate the region in reconstructed energy where the oscillation effect is largest are feed down from events with much higher true energy. Another important point that Mark mentioned is the uncertainty on the electron neutrino cross-section. So typically we're measuring muon neutrinos in the near detectors, but it's electron neutrinos that we see at the far detectors when we're measuring CP violation. And we have a theoretical uncertainty on these. It's roughly estimated to be around 3% or a little bit larger. It depends on a number of things like phase space differences and how different the cross-section can be in the regions where the phase space is different. Form factor uncertainties in lepton mass dependent terms and radiative corrections. You can read more about some estimate of these here. But there is a theoretical uncertainty on the difference between these two cross-sections. So to try to constrain things for hyper-K, we've planned a suite of near detectors that essentially includes 3 different parts. So the Ingrid on-axis detector, so that will essentially monitor the beam rate and measure the beam direction. And then will be a magnetized off-axis detector that's based on the current ND280 detector for T2K and further upgrades of that, both for T2K hyper-K. And that has the capability to measure hadrons below Cherenkov threshold and is also magnetized, so the wrong sign component of the beam can be measured. And then a new detector called the intermediate water Cherenkov detector, which is a kiloton scale water Cherenkov detector that gives us a water target. And as I'll talk about later, we make measurements at different off-axis angles, which is an important feature of that detector. So quickly to comment on Ingrid. So this is it essentially is a cross configuration of neutrino detectors that consist of 14 modules, with each module having alternating iron and scintillator layers and a total of 10 tons of target mass. So essentially this monitors the neutrino or anti-neutrino rate of the beam as a function of the position of these detectors. And from that, we get the beam direction measurement. But it also is monitoring the beam event rate with very high statistics. So if there was some change in the beam configuration that changed the production of neutrinos or anti-neutrinos, we would likely see it in Ingrid first. And then for the magnetized detector, so if you attend Davide's talk on the ND280 upgrade for T2K, you'll learn more about this detector. But T2K is in the process of upgrading the magnetized ND280 detector with a planned installation in 2022 and operation for T2K from late 2022. And this consists of a new target, segmented scintillator target, and so-called horizontal TPCs above and below that target, and time-of-flight detectors that are used to measure particle direction. So the idea here is that we want to improve on this and bring it into the hyper-K era, giving us a well-understood detector at the start of hyper-K, although we think that there will probably be additional upgrades that are needed. So just to give you an idea of what we're getting out of this upgrade, the new time-of-flight detectors allow us better to distinguish the direction of high-angle muons, which is important for measuring the wrong sign contribution of the beam. The high-angle TPCs give full angular coverage, which really wasn't present in the original T2K design. And this super FGD target gives better segmentation in 3 dimensions, which allows for improved spatial resolution in the reconstruction of short tracks, for example, or detection of particles from neutron scatters. And you can see that this is showing the threshold, the efficiency as a function of proton momentum for reconstructing protons. And the red is this upgraded FGD, and the dashed line is the old T2K, ND280 FGD. So there's significant improvement there. Okay, so then I'll move on to the intermediate water Cherenkov detector. So this is a kiloton scale water trank-off detector, and it's located about 750 meters from the neutrino production point. Essentially, there's an instrumented detector in a 50-meter deep pit, and by controlling the water level in that pit, we can actually move that instrumented detector to different off-axis angles away from the beam direction, so ranging from 1 to 4 degrees off-axis. This detector will have new multi-PMT photosensors that I'll talk a little bit more about later inside it. And by making measurements at these different off-axis angles, we can really probe the energy dependence of the interaction cross-section. So, and another possibility for this detector is to load it with gadolinium, as you heard about in the Super K talk. This is now being put in Super K, to have neutron tagging in this detector as well. So the reason we want to make the measurements at different off-axis angles is that we get a different neutrino spectrum as we vary the off-axis angle or the position of the detector. And essentially we can use these as a way to untangle the relationship between neutrino energy and what we observe in the final state. So an example of how we do that is we use these spectra as a set of kind of basis functions, and we combine them with some linear weights to make a very narrow band neutrino spectrum. And then we can take what we observe in the detector as far as the final state charged lepton and combine them with the same weights. And then what we get is a reconstructed energy distribution for the very narrow distribution that we deduce from the spectra that allows us to measure things like the amount of feed down that we see in the spectrum, and do that with precision of about 5%. Another thing that we'll do in this detector is to measure the electron neutrino cross-section. So we do have electron neutrinos and antinon neutrinos in the beam from muon and kaon decays. With enough detector mass, we can get decent statistics on these, and a water trank-off detector is ideal for this because there's large active volume that allows you to veto on what's usually a dominant background, which is externally produced high energy gammas. So there's work done on this type of analysis. This external gamma background is really controlled very well in the water trank-off detector. And preliminary measurements show that precision down to around the 3% level can be achieved, but it does depend on how well we control the systematic uncertainties, particularly on the flux model. So there is work to try to understand if that can be improved. And there's quite a bit of work going on for this R&D for this detector, including the development of, or the testing of different 3-inch diameter PMTs that can be used in this, and actually trying, for example, to find PMTs with very good timing resolution so that we have the performance that we need. The development of a FADC-based electronics readout that actually goes inside this multi-PMT module. So you can see the readout board here on the base plate of one of these modules, and then you can see an assembled module, prototype module on the right-hand picture here. So this is essentially putting 19 PMTs inside a single module that goes in the water, along with the electronics. So there's really only a single cable coming out of this module. So with the better timing resolution and also spatial resolution that comes with these smaller PMTs, we really want to take advantage of them. So there's also quite a bit of work on the application of machine learning to this detector. This is just showing one ROC curve here where you can compare the green line, which is a kind of traditional reconstruction tool, and this orangish yellow line, which is a machine learning based algorithm, and the rejection of a muon background when looking for electron signal becomes much stronger. Okay, so we're developing this new detector. We want to be able to test detector components and make sure we understand the calibration and the performance of this detector. So we actually have planned to build a prototype scaled down version of about 4-meter diameter and 4-meter tall, and put that in a charged particle beam at CERN. And this will allow us to then have fluxes of known particle type and momentum entering the detector, and we can study the detector performance. So this has actually been submitted to the CERN SPSC with the proposal to operate this in the east area at CERN. this is actually a separate collaboration from HyperCase, so others are welcome to join this, especially if they're, of course, if they're interested in water trunk-off detector technologies. Okay, so I think I'm at the limit of my time, so I'll just leave you with my last slide and happy to answer any questions.
Thank you, Mark, for the talk. The questions, I don't see any hands raised. Fine. So let's continue. Thank you again, and let's continue by series of 2 talks about Ptolemy project. First of them is by Marcelo Messina. So Marcelo, please.
Hello, can you hear me?
Yes.
Okay, nice. So
please go on. You have 12 minutes.
This is just a background. I'm not on a boat. I just forgot to have this background. So let's go straight to the topic. So the aim of the Ptolemy experiment, the Ptolemy project, actually is to address the possibility of detecting relic neutrino, cosmological relic neutrino. So why we believe in beaming? Let's try to point out why this cosmological relic neutrino detection can be very interesting. We believe in Big Bangs because we see the expansion, we measure the expansion of the universe. We from the light element abundance also, we have a clear evidence of the expansion of the universe. We also detect the cosmic microwave background that as what remains of the primordial explosion. And what is missing, the last evidence of the expansion of the universe, is a cosmic neutrino background that actually so far escaped the detection. Another very good point why to detect the cosmological relic neutrino is that so far what we know of the universe is just obtained by the measurement of the CMB that decoupled or was created, let's say, 380,000 years after the start of the universe, while relic neutrinos have been created or decoupled 1 second after the start of the universe. This means that looking at neutrino is like looking at a screenshot of the universe 1 second after the start. So this would give us quite many more information about the universe. Some features about these neutrinos. So they have very low kinetic energy according to the cosmological standard model. As you see reported here, the temperature is 1.9 Kelvin. That corresponds to very tiny momentum. The flux is the density of these neutrinos is 56 per flavor. So 56 neutrinos per centimeter cube, and the fluence of the flux of the neutrinos is the largest one that you can imagine, even though the energy of these neutrinos is very little. And you can see here the flux versus energy of the neutrinos from different sources in the universe. So is it possible to detect milli-electron volt kinetic energy neutrinos? Let's see. So in this paper here in 2007 was published this idea that actually was also mentioned long before by Steven Weinberg, but in the paper here they were made clearly calculated the cross-section interaction neutrinos on beta unstable elements. Why beta unstable elements? Because we know that beta unstable, they decay, produce an outcoming antineutrino and electron, but you can imagine this outcoming antineutrino as an incoming neutrinos, and the nuclear transition is the same actually, so the invariant amplitude of the process is the same. What changes the kinematics actually, the fact that neutrino is incoming now, as an incoming particle, this favor stimulate the process, and the signature is the one that is reported here. So the electrons do the neutrino capture actually are expected to accumulate in a distribution here 2 times m nu farther away from the last beam of the Curie plot or the element that we are considering. So you must be able to measure this distance in energy scale in order to be sure that you are observing this neutrino capture. And this was, in the cross-section of this process were explicitly calculated in this paper. And from there, the discussion on this experimental topic restarted. Here you see some more details about calculation. More of these plots will be shown by Stefano Gariazzo in the next talk, where he will discuss more about the physics program, the physics that we can do with this within the Ptolemy project. So Why tritium target? Among the beta unstable elements, we have chosen tritium. Why? Because of a high cross-section for neutrino capture, because there's a sizable lifetime, because when you have a target that is an unstable element, better you have a large cross-section and a large lifetime. So what must be optimized is the product of cross-section times lifetime, and not only the cross-section. Low Q value. And the drawback is that tritium beta actually provides many, many decays per gram, 10 to 15 becquerel per gram. This means that you cannot measure all electrons, but you need to measure only few of these electrons, the one in the region of interest. So the Ptolemy experiments. The goal is find evidence of cosmological neutrino background, making accurate measurement of neutrino mass, and also actually there is some possibility to study light dark matter detection, but this will not be discussed in this talk. And the key challenges are extreme energy resolution that is required and extreme background rates from the target. So the concept here. The concept is that, first of all, we have a new tritium storage capability based on a monoatomic layer of graphene. With the idea is to embed tritium in graphene monoatomic layer such that, and I will tell you why we need this type of tritium storage. Then we aim at transporting the electron from the target place to a region where the RF emission of a single electron in a given field is measured. And this is important because this will trigger a dynamic filter that has the aim of selecting muons in the region of interest. Then at the end of this filter, the electrons are supposed to be driven into these calorimeter detectors where the final very high extreme resolution measurements is realized. So in these slides, once more, the steps of the measurements are summarized with some information, some equations. We cannot discuss this, will take too long. Just quickly, a new way of storing atomic tritium. In the step 2, we have electron RF emission is detected, and this triggers good particle and give a preliminary evaluation of energy and the transverse moment, transverse with respect to the magnetic field line. And in this equation, you see the frequency dependence by the relativistic gamma factor and also the power associated with this frequency. And then in the step 3, there is the filter, the one that is supposed to select the particle of interest, and the field is properly set. In this filter, the field is properly set on millisecond time scale, and so the transverse kinetic energy is removed by pushing the particle on an electrostatic potential here. What does it mean? I mean, we in order to be able to select the particle, we need that the momentum must be straightened on a magnetic field line. Now, how you do adiabatically and the energy stays the same. Otherwise, we find out that there is a way to remove the transverse momentum, and you get a straightened particles with a magnetic field that is decaying exponentially. I mean, just believe me, it's a bit too long to explain here. How does it work is embedded in these equations. And then the step 4 is the one of where the electron is transporting the microcalorimeter and where is realized the final energy measurements. And the good thing is whatever you do in this filter, this would require some time to explain. The final energy of the electron is just the charge times the delta with the voltage at the anode minus the voltage at the source plus the energy measurements in the calorimeter. Whatever you do in the filter, you don't affect the overall energy. And this is the very interesting aspect. Once more, some other little cartoon to try to explain a bit more the feature of this new type of filter that we call dynamic filter. So the tuned particle, the particles of interest for which we set the proper field, they move along this green line here on a straight line trajectory by climbing this equipotential surface. They move so at higher and higher potential at expenses of the transverse momentum. And at this point where the magnetic field is very low, because it is done to decay exponentially, the particle is driven into the calorimeter for the final energy measurements. While the particles out of tune, so you see here out of tune and tuned, they end up on electrons. So naturally, the particles that are out of the region of interest, they found the field that is not properly set, they die on the electrodes, while the particles that are of interest for us, that meet the right field that we set promptly, they go straight and end up in one of the calorimeters at the end. Why we need tritium? Because graphene to store tritium. because when tritium is expected, when tritium gets bounded with the monatomic layer of graphene, this bounding status is expected to be very well defined without any rotovibrational degree of freedom that would deteriorate the energy of the electron when it comes out. While this happens actually when the tritium is exploited in the molecular form. When the tritium is exploited in molecular form, the electron that is emitted by the tritium decay actually suffer of smearing due to the rotovibrational degree of freedom of the molecule that can be activated. This phenomenon does not exist in the graph, is not expected actually. This is a theoretical prediction that is not expected, but this is something that we should measure. On the right, a picture of the system that can make the embedding of the tritium in the graphene layer. Here you see there is a big effort in simulation the signal of a single electron detected by resonant cavities of waveguides, and we need a lot of effort here to be able to detect this very low power. The power we're talking about is on the scale of, it's just the square of this number, so it's on the scale of femtowatt and less than femtowatt. Anyway, there is a big effort in simulation and optimizing the geometry of this RF antenna. Here are some details of the magnet. It is one of the most important and difficult things to design. The magnet should be able to accommodate the target, the RF region, and then this is the filter region in which the B field must have an exponential decay such that naturally in the region of a microcalorimeter that actually are TES, transition edge sensor, the field is sufficiently low. And also here is a big effort in simulation, all the things that we need. Microcalorimeter, the final detector, the benchmark is this microcalorimeter, this performance that have been proved by the National Institute of Metrology, where they run what is a microcalorimeter is represented here. There is a bulk where energy can be absorbed. This bulk is in thermal contact with the bath, so at a fixed temperature, and the temperature jump due to energy release in the bulk is read out by a TES, transition edge sensor. It's a superconducting strip that when gets warm, gets at higher temperature, makes the transition from superconducting to conducting, making a big jump in the current flowing. The resolution that has been shown by this by the Italian Institute of Metrology is this one. Actually, this is a full width at half maximum 0.12 electron volt. That is 50 milli electron volt energy resolution. This is a picture of the TES. The challenge is making this TES definitely larger, up to 100 micron squared, and keeping similar resolution. This is a picture of where we have our, let's say, R&D facility at the moment at the Gran Sasso, in the Gran Sasso laboratory in Italy. This is where we are now, above ground, not underground for the moment. This is a picture of some magnets and some devices in our above ground side. This is a list of the institutions that are expressed interest for this project: 7 countries, 23 institutions, and more than 50 physicists. And so to conclude, it's something completely different. Physics program matters to relic neutrinos, light dark matter neutrino mass, technological challenges, and new support for tritium, extreme energy, high rate, and extreme energy solutions. And here there are 2 papers in which our recent results are summarized. So the last 2 words to just thank the organizing committee for inviting me, and also the people for listening. That's it. Hello? Sorry, I can't hear anybody.
I don't think anyone is talking, unfortunately.
Hello? I'm sorry, but I don't hear any message. I assume that you move to the next speaker.
Yeah, I think we can move to the next speaker, which is going to be Stefano Gaiazzo talking about the Ptolemy again.
Okay, so I will share my screen.
So go ahead when you're ready.
Yes. Can you see my slides?
Yes, we can see it.
Okay. So in this talk, I will discuss about the physics that the Ptolemy experiment can explore. So let's start from the beginning, that is an introduction of the cosmic neutrino background. So we know that the history of the universe is well described by a model where the Big Bang was an initial state with a very high temperature that give rise to the expansion of the universe. So the current universe is the result of an expansion that is initially driven by an inflationary phase. Then there is a phase where all the particles are in mutual interaction between each other. But while the temperature drops, some of them start to decouple. And in particular, today, we observe the relics of the cosmic microwave background, that are the photons that decoupled when the temperature of the universe was around 0.3 electron volts, and the BBN, that they are the light elements produced when the temperature was about 0.7 mega electron volts. Just a little bit before the Big Bang nucleosynthesis, there was the decoupling of neutrinos. Neutrinos decoupled when the interactions with electrons are not strong enough to maintain them in equilibrium. And in particular, it's possible to compute that expanding a universe until today, the temperature of the neutrinos decreases. And decreases up to the level of 10 to the minus 4 electron volts. It's like 0.1 milli electron volts. Such neutrinos are the most abundant particles in the universe, apart for the cosmic microwave background photons, with a number of 56 per centimeter cube per family. And we also know from neutrino oscillation constraints on the neutrino masses that at least 2 of the mass eigenstates are non-relativistic today, because their mass is larger than their average energy. So we know very well the universe until the epoch of the CMB, because we have an image of the anisotropies. This is a comparison of the first images of the anisotropy from COBE, then the WMAP one, and then the Planck, the most recent map. On the other hand, we have no observation of the relic neutrinos. This is what we would like to achieve. It's a technologically complex challenge, as Marcello already said. But this would give us the image of the universe when it was 1 second old. So much older than with respect to what we know from the CMB. We know that the cosmic neutrino background is likely to exist because we measure this number of effective relativistic species in the universe, and effective, which is predicted to be 3.0 something. It's not exactly 3 because the neutrinos do not decouple instantaneously. There is a little bit of energy transfer from the electrons when they become non-relativistic. And this 3.04 something is in perfect agreement with the experimental value by Planck, for example, 3.0 plus minus 0.2. So this means that we have an indirect probe of the existence of the cosmic neutrino background, more or less 10 sigma or even more, depending on the exact data set that is considered. So we know that these neutrinos are likely to exist, but we would like to really detect them in a direct way, because in this, with an indirect probe, we do not know if this n effective equal to 3 is just coming from neutrino or there is something else. How to do that? Well, it's complex. The best idea is to use the neutrino capture on beta decay nuclei. So instead of having a nucleus that can undergo beta decay when a neutron decays into a proton and electron and an antineutrino, we can have that the antineutrino is in the initial state as a neutrino. So the production of the electron is triggered with the energy that is higher than the endpoint of the beta decay. Particularly, we see in the figure that there is on the left the beta decay spectrum that goes down until the endpoint, that is K end.
which depends on the neutrino masses because the neutrino takes part of the energy. Plus, we see a peak that is due to the neutrino capture of relic neutrinos. And in particular, you see that the distance between the new peak and the endpoint of beta decay is twice as large as the neutrino mass. In this figure, I am assuming that the 3 neutrinos are degenerate in mass. There are 2 problems. So the first problem is that this peak is much smaller than the beta decay spectrum. So we have to achieve an impressive energy resolution in order to detect the signal from the background. And we need a lot of material. If we write the spectrum for cosmic neutrino background capture, it will depend on the number of target atoms. It depends on the mixing matrix element because each of the mass eigenstates will contribute differently. It depends on the average number of neutrinos in the universe, but also it depends on this FC is a clustering factor that depends on the mass of the neutrinos because the neutrinos can cluster in the dark matter halo of the Milky Way, for example. This is the expression for the beta decay spectrum, and this is more or less what we could observe, assuming that the lightest neutrino has a mass of 10 millielectron volts, and this energy resolution is also 10 millielectron volts. So we see that if the neutrinos are distributed according to the normal ordering, where the lightest neutrino is the one that has the largest mixing with electron flavor, the first peak from the cosmic neutrino background, that is this one, is closest to the beta decay spectrum, so it's hard to distinguish this peak. And the second peak is much smaller just because of the value of the mixing angles. In the inverted ordering case, it would be the opposite. So the first peak is much smaller and it's easier to detect the second one because it corresponds to a larger number of events. Unfortunately, this is for a very optimistic energy resolution. If we go to a less optimistic energy resolution, we see that it is crucial to have an energy resolution comparable with the lightest neutrino mass, because otherwise all the events will be lost behind the beta decay spectrum. It's impossible to observe them. So the idea is that the Ptolemy experiment, it was already discussed in the previous talk, with 100 grams of tritium, we'll try with an energy resolution of 0.05 electron volts or so to detect something like 10 events per year from the cosmic neutrino background capture. This number could be enhanced a little bit. I will not discuss the neutrino clustering and other effects because I have no time, but I will now move to the results. So I will not discuss the structure of the experiment because it was already part of the previous talk. Let me go to a few formulas that we used for the simulations. So basically we compute an expected number of events, assuming a fiducial energy, fiducial mass, and fiducial mixing matrix for the neutrinos. And then we use this expected number of events to try to fit the theoretical expectations. And this will depend on the amplitude of the beta spectrum that we leave as free, on the amplitude of the neutrino capture spectrum that is also left as free, and then of the masses and the mixings on a constant background, and even we fit a possible shift in the endpoint. So if we compute this chi-square, we can do a study and study the sensitivity of the experiment in the different cases. And we started from the neutrino mass determination. Here we assume a fiducial value for the lightest neutrino mass, and we vary the lightest neutrino mass and the energy resolution. This is what we would observe with the full-scale Ptolemy experiment with 100 grams of tritium. Statistical errors are only taken into account because we have no information on the systematics yet. But let's say an ideal direct detection experiment with 100 grams of tritium can achieve at most 1% measurement of the lightest neutrino mass if it is 10 millielectron volts. Of course, this will be much worse with the systematics if they are not under control, but this is an idea of what the ideal experiment can do. We can compare normal ordering, inverted ordering. We see that there is basically no difference. And also the energy resolution does not influence very much the result. It's interesting also to consider like preliminary or prototype Ptolemy experiments with less tritium. This is 1 gram, and this is with 10 milligrams. This could be like the first phases of the development of the full-scale experiment, and we can see that even with just 10 milligrams of tritium, we could have a detection of 2 or 3 sigma of the lightest neutrino mass, even if it is of 10 millielectron volts. The sensitivity is probably like 7 millielectron volts or something like that. The second study we did is that, as you may remember from these plots here, there is quite a difference between normal and inverted ordering. And the difference is especially visible here because there is a kink that is due to the fact that the mixing matrix elements are exchanged in the normal and inverted ordering. So the second lightest neutrino is much heavier in the inverted ordering case. And this is why the kink is much more visible. So just due to the fact that we are observing so many beta decay events, we use the Bayesian method, but what we obtain is that it's basically extremely easy to measure the mass ordering because the difference in the number of events from the beta decay spectrum is huge. We did not study this case with the smaller scale experiments, but it will be similar. So the difference is really, really huge in the number of expected events from beta decay. The crucial point is that actually Ptolemy is built in order to detect the relic neutrinos. And the detection of relic neutrinos, we estimate the significance by fitting this parameter here, that is the amplitude of the cosmic neutrino background spectrum. If we can detect this parameter to be larger than 0 at few sigma, we will have a detection at few sigma of the cosmic neutrino background. And here I show the comparison of the sensitivity in normal ordering and in inverted ordering cases as a function of the energy resolution and of the lightest neutrino mass. The blue region is what corresponds to less than 1 sigma detection, so basically no detection, while the orange would be a 3 sigma detection. And you see that even with 100 grams of tritium, it's very hard to have a clear detection of the cosmic neutrino background. We would need heavy or relatively heavy lightest neutrino mass above like 0.1 electron volts, 0.15, something like that, in order to have a 2-3 sigma significance. And even more crucial is the dependence with the energy resolution. So if the lightest neutrino mass is below, say, 20 or 10 millielectron volts, we will really need to achieve a much better energy resolution than what we are expecting now. In this case, we do not study the perspectives with less than 100 grams of tritium because it would be absolutely impossible. The number of events is too small in order to expect to be able to reconstruct this parameter here. So in conclusions, we have seen that Ptolemy can see the neutrino masses, the mass ordering, and in the most optimistic case, even detect the relic neutrinos for the first time. The requirements for the experiment are not that strict if we want just to have a first detection of the neutrino masses or of the mass ordering. But so the preliminary, the prototypes would probably already be able to do a lot of physics. If we want to do the relic neutrinos, then we really need the full scale experiment. So to summarize, this is a very complex technological challenge. It would be an amazing result because it would be the first time the non-relativistic neutrinos of the cosmic neutrino background are observed. And meanwhile, we can also study neutrino masses and mass ordering and so on. The problem is that we have to develop all the technology, as Marcello already discussed. Thank you very much.
Thank you for the talk. Are there any questions? Yes, I don't see any. I think we can go to the next talk by Feifei Huang about the Neutrino astronomy prospects. Please go ahead and start when we are ready.
Hello. Hello. Can you hear me? Well,
yeah, we can hear you.
Okay, great. Let me share my screen. Okay, can you see it?
Yeah, we can see it.
Okay, great. All right, so hello, my name is Feifei. I'm going to present you the status and prospects for neutrino astronomy search with CHEM3net. So I will mainly talk about these 4 aspects, and I will show you the status and some first measurements with our detectors. So let me first go to the introduction part. So this is a map of our collaborators all over the world. We have over 200 scientists spanning over 4 continents. The yellow dots here represent the locations of our detector sites. I will talk more about this later. So this is an artist impression of one building block of our experiment. So one building block consists of 115 strings attached to anchored to the seabed, and each string has 18 DOMs. And here one DOM, the DOM refers to the digital optical module, and it consists of 31 3-inch PMTs beside, facing at different directions. So basically our detector is this 3-dimensional array of optical sensors that are able to detect Cherenkov light emitted by the secondary particles from the neutrino interactions in water. So for example, here is a muon neutrino coming, having interactions here, and the outgoing muon track goes through the detector and produces the Cherenkov light. This is the Cherenkov cone it created, and by using the arrival time and amplitude of the observed light in the DOMs, we can reconstruct the neutrino direction and energy. And we can have a very accurate positioning up down to like a few centimeters level, and the timing resolution of 1 nanosecond. And this guarantees a accurate and precise direction reconstruction that are important. Okay, so now this shows again the detection sites. So we use a phased construction for our detectors. So right now we're in phase 1. Where we plan to have 6 strings of Orca and 24 strings of Arca. So Orca is located in the sea near France. Here, it has, relatively speaking, a dense spacing. So here, the 115 strings are distributed within like 100-meter radius. And on the right here is Arca, which is located near Italy. It has a sparser spacing, and it's sensitive to neutrinos in above 1 TeV range. So let me show you more in detail what the science goals are for CHEM3net. So this is a the neutrino flux for different neutrino sources, either naturally occurring or artificially made, and over a large energy range. So this blue shaded area is our region of interest. And for Orca, our main goal is to measure the atmospheric neutrinos relatively in GeV to TeV range. We want to look for neutrino oscillations, determine the neutrino mass hierarchy, neutral appearance, etc. We also can conduct some low energy astronomy for time or space clusters. Then for Arca, we want to detect astrophysical neutrinos that are very energetic. So more specifically, for example, neutrinos in galactic point sources or diffuse astrophysical neutrinos flux. Also for the multi-messenger astronomy, we would like to send and receive alerts for transient source searches. Then at the MEV level, we are also sensitive to MEV supernova burst neutrinos. Here I say both Orca and Arca because one single dome can act as a detector. So today I will show you our results regarding these 4 bullet points. Before I do that, I will show you the neutrino signatures which we expect to see. So we divide them into 2 channels. One is track-like events, where we see events with a visible muon track. And so with this muon track, we can see this simulation here, which created this light path inside our detector. And this provides a great pointing resolution for points like a neutrino source study. On the right here shows the shower-like events, where there's no visible muon track, and the light distribution is more or less symmetric, and but we can still achieve quite nice angular resolution. So this is just more in detail the reconstruction resolutions. I'm not going to spend too much time here. But basically, this is the in the track channel we see the good angular resolution we see here, especially above 100 TeV. All right, now let's talk about the studies we can do. So first, for the diffuse neutrino flux, we want to detect astrophysical neutrino flux. They're located usually like above 100 TeV range. This is the assumed flux spectrum. And here, this plot shows you the significance versus observation time. And we can see, so with the black curve is the search with 1 block of ARCA, and the blue is for the full blocks, the 2 blocks of ARCA. So you can see we can already achieve 5 sigma of significance within 1 year with 1 block, or half of a year with 2 blocks. Then for point-like neutrino searches, so this is for sources with a generic neutrino flux proportional to e⁻². So for example, here I'm comparing the KM3net sensitivity with ICECube. The x-axis here is the source declination. So here on the left, this is the southern hemisphere, and this is the northern hemisphere. Because KM3net is located in the northern hemisphere, we have a very good sensitivity to sources from below us. So we can see that we can achieve an over 1 order of magnitude better than ICECube in this range. All right, now we also considered extended galactic sources. So these sources are known gamma ray sources, and we used neutrino flux derived from the gamma ray flux. So here you can see in this plot the discovery potential versus observation time. So for example, for this Vela Junior source, we would be able to achieve 3 sigma significance within 6 years. And similarly for this RXJ source. On the right side, this is a stacking analysis, including both, and we can see a 3 sigma observation within 3 years. And you can see more details in the link to the paper here. Then for neutrinos, that's my third part. So the most prominent neutrino, supernova neutrino we have seen is these 1987A neutrinos. And so here there are like 25 neutrinos observed that occurred 2 to 3 hours before the light arrival. And future events, we could see thousands of events, neutrinos. Then, so this is showing the sensitivity for KM3net. So the technique to do this, to search for supernova neutrinos, is via the multiplicity, which is defined as the number of PMT hits within a coincidence window inside a dome. So here this plots the event rate as a function of the multiplicity for the background shown in the blue triangles and the signals. shown in these red and orange and light yellow histograms. So you can see, for example, at 7, we see less than 10 like backgrounds from within our detector, and for the signal is over like 10 to 100 events, and the same for the others. Then on the right side here shows the sensitivity versus distance. So you can see for different sources of supernova considered. So for example, at 20 kiloparsec here, we can achieve over 5 sigma sensitivity. For most of the, this covers like over 95% of the galactic supernova sources. And also, I want to mention that CCSN search is also very important in multi-messenger community. So CAM3net is already connected to the SNEWS network. So, all right. Now, let me talk about the multi-messenger astronomy studies. So, in the past, we have seen like 3 successful multi-messenger detections. The supernova 1987, then in 2017, the gravitational wave and electromagnetic observations. And the third one is the famous blazar texts, also in 2017, with neutrinos and gamma rays. So this is really an exciting new area, and CAM3net would like to participate in this, and the goal here is to be able to have a framework to receive external alerts and perform online neutrino correlation search within CAM3net, and or we send online neutrino alerts if we see something interesting, such as multiplets or high energy events in CAM3net, and for external observatories for them to do follow-up. So this requires a fast online reconstruction and a fast selection of high purity neutrino sample. So here I'm showing you the status of the framework here. So currently since we have 6 lines of ORCA, here shows you some of the time it takes for doing online reconstruction. So it right now is less than 1 second per event for a standard track direction reconstruction. And for shower reconstruction is on the order of 1 second per event. Then for online event selection, right now, we are using a gradient boosting decision tree for event classification, and it costs less than 1 second per event too. So here I'm showing you a preliminary selection with this BDT, and here it shows you the effective area with 7 lines of ORCA, and we see we can reduce the background by 100,000 times while keeping 30% of our neutrino signals. On the left here is the plot showing the angular resolution versus energy. This is again for 7-line ORCA. And you can see with this selection, we can achieve at 1 TeV a 1 degree angular resolution. And then for the time delay here right now, with the online filtering plus the online reconstruction and online event selection, we achieve roughly 4 seconds of time delay on average. All right, now let me show you some more recent news. So CAM3net is being reconstructed. So the current setup is we have 6 strings of ORCA running. So this is phase 1 since this year, January. And then ORCA has 2 strings installed. It's now temporarily shut down for a major intervention and refurbishment. The goal here is to complete the phase 2 construction within like 4 and 6 years. So right now with these 4 lines of ORCA, I'd like to show you some events simulation inside our detector. Let me just quickly go to this link here. You can see a YouTube link. I'm just showing you this is the reconstructing track going upward in our detector. and you can see the Cherenkov cone coming through and lighting up our DOMs inside our detector. So let me go back. And this 6 plots here shows you the triggered hits Z position versus time. And the yellow curve is the earliest Cherenkov light expected from the reconstructed track. So you can see that this is basically the projection of the Cherenkov cone onto our strings. So you can see that they match well with the triggered hits. All right, and then we also have 4-string ORCA data over 4.5 months of lifetime. So here is an event sample with 99% purity. There are upgoing track-like events. So on the left here shows the dashed lines shows you the events distribution before selection. So this is the majority of the events are the background atmospheric muons plus some noise. And then after the selection, we see this is the solid lines. The red is for the neutrinos, and the background is almost removed, and the black line is the data. So even with this 4 months of data, we can see already see the oscillation effect. So here, this yellow curve here is the no oscillation null hypothesis, and we can see that we can already see oscillation at a 2 sigma significance. All right, we also have conducted atmospheric muon flux measurements. So this is the link to the paper. So basically what we're plotting here is the measured muon flux versus depth under the sea. So the red dots here are from ORCA, and these are from ARCA. And the dashed line is the model, theoretical model, and you can see that the data matches the model quite well. And this shows us that we have a very good understanding of our detectors. All right, this is my summary. So having a great angular resolution and with the galactic center in view, KM3 will contribute enormously to the neutrino astronomy. Then for physics with ORCA, please go to this ORCA talk by my colleague, which will happen on Friday morning. And right now we have deployed phase 1 ORCA data with 6 strings running for 6 months. So here are our little celebrations. There are like 2 links for some music instruments playing. For example, this one is for original song, and this is a piano piece. So feel free to have a look when you're free. And we plan to start our deployment soon, and hopefully we will finish the construction of phase 2 within 4 to 6 years. And stay tuned for more physics. Thank you.
Thank you, Feifei, for a very nice talk. Unfortunately, we don't have time for discussion. So the next talk is by Fabio Mantovani about geoneutrino results from Borexino. Please be so kind, try to keep your time.
Okay, do you hear me? Yeah.
Very weakly.
Really? Now? Do you hear me?
Yeah, okay.
Okay, and do you see my screen?
Not yet.
Yeah, now?
Yes, fine.
Okay, thank you. Okay, well, yes, I'm Fabio Mantovani, and tonight I would like to present the recent improved geoneutrino result from Borexino on behalf of Borexino collaboration. Well, quickly, the summary of my presentation. First of all, I would like to introduce the geoneutrino and the heat power from the Earth. In a few words, the idea is to understand what happened thermal history about our planet. And then I will present the recent result from Borexino. And finally, we will see what are the geological implications of this measurement, and which are reported in a complete paper which is published at the beginning of this year on Physical Review D. Geoneutrino, what are geoneutrinos? Well, by definition, are the antineutrino producing by beta decay inside the Earth. In particular, uranium, thorium, and potassium in the Earth release heat together with antineutrino in a well-fixed ratio. Here I report the free measured contribution to the natural radioactivity of terrestrial in the Earth, and uranium decay chain include 8 alpha decay and 6 beta decay, which produce antineutrino with a maximal energy of about 3.3 MeV. And as you can see here, there is a fixed ratio between the radiogenic heat power produced by uranium and antineutrino luminosity. The same is for thorium, which has a lower maximal energy. Concerning potassium, the maximal energy of antineutrino is below the threshold of inverse beta reaction, which is used for detecting geoneutrino. Here I report the inverse beta reaction, which is basically an interaction between antineutrino and a free proton, which produce a positron, which is the prompt signal, and neutron. And the threshold is 1.8 MeV. We can recognize 2 different energy contribution from uranium and thorium, since the highest energy come from thorium and geoneutrino. And typically the signal is reporting in TNU, which is at 1 terrestrial neutrino unit, which is 1 event per 10 to 32 free proton per year. Let me summarize the open question about natural radioactivity in the Earth. First of all, we don't know what is the radiogenic contribution to terrestrial heat production. And so we would like to know that. And we would like to know also how much uranium and thorium are in the crust and in the mantle, assuming that in the core, we don't have uranium and thorium, because the core is basically metallic based. The third question is about the thermal condition of the Earth initial stage. And what is hidden in the core of the Earth? Maybe a georeactor, maybe potassium-40. And finally, what is the standard geochemical model consistent with geoneutrino data? The heat power from the Earth is basically measured on using 40,000 heat flow measurement, in particular in the continent. But as you can see here in this map, which is published by Davis and Davis in 2010, the highest contribution comes from the oceanic floor, which release about 70% of the total terrestrial power. In order to fix in our mind the order of magnitude, the global heat loss is measured in terawatt, and the scientific community adopted 47 terawatt, which as a power of the Earth. So, what is the origin of this heat? Well, if we neglect the tidal dissipation and gravitational contraction, the two major contributions come from secular cooling caused by the initial hot environment of early formation stage, and the radiogenic heat, which is basically the heat produced by uranium, thorium, potassium inside our planet. It's useful to define the convective Ure ratio, which is basically the ratio between the radiogenic power in the mantle, which is the total radiogenic contribution minus the radiogenic contribution from the continental crust, divided by the basically secular cooling contribution. Why we subtract the radiogenic contribution from the continental crust? Because we can measure in the sample the uranium and thorium abundance in sediment and the upper crust and the middle crust and lower crust. Don't forget that the deepest hole that ever been dug in the earth is about 12 kilometers deep. So we directly investigate only the thin part of our planet. And this part is called the lithosphere, which is the superficial portion of our Earth, which include the crust and the continental lithospheric mantle. Here you have a scheme of the Earth. In this, you recognize the metallic inner and outer core, and then the mantle, and finally the lithosphere. The lithosphere contain less than 2% of the Earth mass, but about 50%, half of the total uranium and thorium mass. In particular, in the continental portion of the lithosphere, in which we can observe uranium and thorium in abundance of some ppm. And this, the lithosphere produce about 12% of the total heat flux. And we know this, this number pretty well using direct measurement on the rocks. So now let me speak about geoneutrino signal. And the first thing to say is that the flux of geoneutrino of the detector located scale with the inverse of the square distance of the emitter. This means that it's important to study the local contribution. For this reason here, I report this green portion around Gran Sasso. And in fact, we observed that 40% of the total signal come from a region which is very close to the detector. And moreover, since we would like to understand the radioactivity in the mantle, we have to consider that the radioactivity, the signal from the mantle is the same order of this small portion around the Gran Sasso area. So Borexino, as you probably know, is a liquid scintillator experiment, which is located in the center of Italy in the Gran Sasso lab. Basically, the detector has a concentric multi-layer structure. The outer layer serves as a passive shield against the external radiation, as well as active sharing convector of cosmogenic
Fabio, you have 5 minutes.
Yeah, and the scintillator, the inner portion of and the active portion of the detector is inside the inner vessel. Here you see the recent result of Borexino detector, and compare it to the previous result. And In this new release, what has improved basically improved the muon veto for internal muon cylindrical veto is applied. And that time are tuned according to the muon probability to form spallation products, which mimic the inverse beta reaction. And moreover, the tagging efficiencies increase, and moreover, we increase also the fiducial volume of the detector. Here you see the distribution of events in the lower energy, in the lower window of energy of Neutrino and the highest energy window. Here I report the background measuring in Borexino. And finally, this is the spectrum in which we collect about 154 anti-neutrino data. And the background is about 8 events, and the geoneutrino and the reactor events, which is the violet area, is 39 events. And in the lower region, you can recognize the geoneutrino contribution, which is about 53 events. And so then you can convert the events in TNU. And then if you assume to know the contribution from the lithosphere, you can extract the mantle contribution. If you want to understand what are the implications of this measurement, you need to compare this contribution with the standard model of the Earth, which is summarized in this slide. The basilic Earth describes the primordial non-metallic Earth. And here you can see the cosmochemical model, which is a lower, has a lower contribution in radioactivity, and the geochemical model, which is the standard model of the Earth, and the geodynamical model, which higher contribution. And fully radiogenic is the idea is the model which is based that all the 47 terawatt come from radioactivity. If we compare the geoneutrino measurement of Borexino with the models, you can see that the observation favor geological model that will predict a relative high concentration of radioactive element in the mantle. And here I reported the measurement of the Borexino respect to the different author hypotheses with the contribution from the lithosphere, the contribution of radioactive from the mantle, and the secular cooling. And an hypothesis, an hypothetical 2.4 terawatt reactor in the center of the Earth is excluded at 95% of confidence level. Finally, here I summarize the result, which are published at the end of the last year from the two main experiments for geoneutrino, Camland and Borexino. And let me conclude with 4 highlights. Then geoneutrino measurement of Borexino is obtained with an optimized data selection, which improved the detection efficiency of 87%. Borexino observed a geoneutrino mantle signal, and the null observation is excluded at 99% of confidence level. Moreover, Borexino estimate for the first time a radiogenic power from the mantle, which is basically 24 terawatt, and the total radiogenic contribution of the Earth. And we observe a 2.4 sigma tension with the basilic Earth model, which predicts the lowest uranium thorium abundance in the mantle. Thank you very much.
Thank you, Fabio. Very nice talk. And as before, we don't have time for discussion. So the next is Michal Danielov talking about dance experiment.
Hello.
Hello.
Hello. I'm not allowed to share my screen because it is blocked by other participant. No.
Fabio, could you please stop sharing your screen?
Yeah.
I did it. Okay.
Okay. Do you see my?
So please go on. Please keep the time.
Okay. Good. Sorry. I will talk today about new results from the DANCE experiment. Many extensions of the standard model have sterile neutrinos. There are also experimental hints of sterile neutrinos. A deficit of reactor neutrinos and neutrinos in calibration runs of the gallium solar neutrino experiment can be explained by oscillations of electron neutrinos to sterile neutrinos. The appearance of electron neutrinos in muon neutrino beam can be explained by oscillation of muon neutrinos to sterile neutrinos and back to electron neutrinos. Recently, the Neutrino 4 experiment claimed the observation of the sterile neutrino with very large mass difference of 7 mass square difference of 7 eV squared. And the neutrino excess in neutrino muon neutrino beam reached 6 sigma level. So this is a very active field, and there are many experiments searching for sterile neutrinos. DANCE is a 1 cubic solid scintillator detector, which is built out of 2,500 1 meter long scintillator strips covered with gadolinium containing paint. Strips in adjacent layers are placed in an orthogonal way. This allows a quasi 3D reconstruction of event. Detector is surrounded by passive shielding and active muon shielding. The detector is installed on a movable platform on the 3 gigawatt reactor of the Kalinin nuclear power plant in Russia. The material of the reactor provides a shielding which reduces the cosmic background. The detector distance from reactor is changed 2-3 times a week from 10.9 to 12.9 meters. We made many improvements since the previous analysis, but the major change is that we use not only the shape of positron spectra at different distances, but also relative rates. This improved the sensitivity of the experiment. We also use 3 detector position in the feed. This gives a very small gain in sensitivity, but provides a cross-check of for the consistency of the data. Previously, this was done separately. We collected about 4 million IBD events, mainly at the top and bottom detector positions, which are most sensitive to neutrino oscillations. Accidental coincidence background is determined directly from the data and subtracted in a model-independent way. However, it increases the statistical errors. Therefore, several cuts are applied in order to reduce it. For example, the cut on the distance between the prompt and delayed signal. This cut depends on the energy of positron. For small positron energy, where we have a lot of background, this cut is more tight, and this allows us to reach a very reasonable fraction of the accidental background of about 14%, keeping high efficiency for the signal. Cosmic muons are rejected by muon veta. However, this system, muon veta system, has some inefficiency, and this inefficiency was determined using the reactor of data. Finally, the total amount of background we have to subtract is about 1.7% at the top detector position. That means we have the signal over background ratio of larger than 50. Muons are used to calibrate continuously all 2,500 scintillator strips, and also they are used to check the linearity of the detector response. The energy scale of the experiment is anchored by the boron 12 decays. Electrons from these decays are very similar to the positrons from IBD events. I must stress that we measure only kinetic energy of positrons. We do not use annihilation gammas because they produce many soft electrons, and these soft electrons lead to a non-linearity of the signal. In addition to the boron 12 calibration, we use several other calibration sources just for to cross-check the result. And here you see the signal from the neutron capture on gadolinium, and below is a spectrum of Michel electrons. This calibration source is very interesting because we have many Michel electrons, more than 10,000 per day, and therefore we can check the calibration dependence on time. Here you see the positron spectra measured at the top, middle, and bottom position, detector position. At the top, we detect about 5,000 events per day with a background of 1.7%. We compare this shape of the positron spectrum with the prediction of the Huber-Muller model. In order to reach the best agreement with the model in the region between 1 and 3 MeV, we shifted the predictions of the model by 50 keV. With such a shift, we see some bump similar to bumps in other experiments. However, we cannot claim that we observe such a bump because the spectrum shape depends very strongly on the energy scale and on this shift, for which we do not know the reason. Here you see a comparison between the reactor power shown in blue and red and counting rate of IBD events. You see the nice agreement. Obviously, we corrected the counting rate for 1 over R square dependence and also for fuel evolution using Huber-Muller model. Also, we subtracted a very small background from adjacent reactors. The spread is very small, and we can say that we measured the reactor power with the anti-neutrino flux with 1.5% accuracy in 2 days during 3.5 years. The spread of points is consistent with just statistical nature of this spread. The test statistic consists of 4 pieces. The first term is related to the period when we used 3 detector positions for measurement, top, bottom, and middle. The second term corresponds to the period when we used only top and bottom positions. The third one takes into account relative energy, relative efficiency, and finally, the last term takes into account different systematics. Systematics are treated as nuisance parameters during chi-square minimization. Here you see the difference in chi-square for 4 new and 3 new hypotheses. The red regions are regions with chi-square for 4 new hypotheses smaller than for 3 new hypotheses, and the blue one is opposite. The dark blue region corresponds to a 3 sigma confidence level exclusion in case of chi-square distribution with 2 degrees of freedom. However, this assumption is not valid, and we use Gaussian CLS method to get limits. Here you see the ratio of positron spectra at the bottom and top position and middle and top position. Blue lines correspond to 3 new case, and magenta lines correspond to the best fit for the 4 neutrino hypothesis. It has a chi-square smaller by 5.5. However, this difference is not statistically significant. It is only 1.5 sigma significant. The yellow line is the prediction for the best fit point for reactor antineutrino anomaly, and it has been excluded with a delta chi-square of about 68. I would like to stress that this point was excluded by Dance with more than 5 sigma already 2 years ago. The exclusion region was calculated using Gaussian CLS method, and the corresponding sigmas for nuisance parameters and corresponding systematics are shown here. The new data allowed and new analysis allowed to extend the excluded area in the 4 neutrino parameter space, and we exclude a very interesting area with a lot of predictions there. I would like to stress that the most stringent limit reaches already 8 times to the -3 in sine square of 2 theta. We plan to upgrade the detector. We plan to use strips with 8 fibers. In this case, the uniformity of the response is very good, and also light yield is sufficient to get the desired resolution. And with the upgraded detector, we can check the neutrino 4 claim in 1.5 years of data taking. So this is my conclusion. With improved data analysis, Dance records about 5,000 antineutrino events per day with a cosmic background of 1.7%. That means with a signal over background ratio more than 50. Reactor power was measured using antineutrino rate with statistical error of 1.5% in 2 days during 3.5 years of operation. Dependence on the fuel composition was clearly observed. There is an indication of 5 MeV bump, but it is not conclusive. And preliminary Dance analysis based on 3.5 million of IBD events excluded a large and very interesting part of the 4 neutrino parameter space. I think that's all. Thank you for your attention, and thank you for organizers for inviting me to give the talk.
Thank you. Congratulations to the nice results, and for keeping the time. No questions are, no hands are raised, and so let's continue with the next talk. It is by Xianyi Zhang, who is going to talk about reactor neutrino measurement with Prospect. So, Mikhail, please unshare the screen. Thank you.
Can you see my screen?
Yes. Please go on.
Okay. So thank you for the introduction. I'm presenting on behalf of Prospect a collaboration about our improved reactor antineutrino measurement with Prospect. Prospect's motivation includes a model-independent search for the EV scale stereo neutrino that's been suggested by reactor spectrum measurements around the world, and some short baseline accelerator experiments as well. And we want to measure the EV scale stereo neutrino in a very short baseline model independently, and we measure the uranium-235 spectrum from HEU to provide the insight into the fission isotope source of the spectral difference in C between the data and model that's been measured by different commercial reactor at different commercial reactors, and we commonly call it an excess at 5 MeV. Oops. Why is it not moving? Okay, the detector, the experiment, we observe the antineutrino from the HIFER reactor, where 99% of antineutrino are from uranium-235. It's a compact core where the width and height of the cylindrical core is about a meter and is about ½ meter, and the reactor on cycle is about 24 days, and reactor off cycle is about a month. They switch on and off constantly while we are in this period while we are measuring the neutrino. And the detector is 4 tons lithium-6 loaded PSD capable liquid scintillator, and the baseline coverage is of the detector is
Hi, Xianyi. Sorry, we only see your title page. It's not moving forward.
Sorry.
Yeah, now we see it.
Can I try the full screen mode again? Do you see it change?
Not really. This works fine.
Sorry. I don't know what to improve this. Maybe I'll have to show it this way then.
Probably.
I'm sorry about that. And let's continue. So we are very short baseline close to the reactor, and we are at high exposure to the cosmic ray at with only 1 meter water equivalent overburden. The detail about the detector is it's optically segmented into 14 by 11 segmentations, and each segment is about 1.2 meter long. This allows us to 3D reconstruct the events position. And the lithium-6 loaded scintillator has a PSD capability to for us to identify the neutron capture and nuclear recoil events, among other events. And both ends of each segment are coupled to 5-inch PMTs, and the long sides are enclosed by specular reflectors, and 3D printed rods are made hollow, so the calibration sources can fit through and calibrate the detector inside. The calibration done, the detector calibration is done with both radioactive calibration sources, gamma sources and neutron sources, and the cosmogenic events like boron-12 to calibrate the energy and position reconstruction. And the detector nonlinearity is adjusted in Monte Carlo simulation. So based on these energy scale calibration, so the simulated nonlinearity has a good agreement with the actual detector energy response. And we achieved person level uncertainty and stability of both the energy and position reconstruction. The way we detect IBD from the antineutrino is to tag the IBD events using time coincidence between a positron event and a neutron that's captured by lithium-6 about 50 microseconds later than the positron signal. And using PSD, we can very easily distinguish the prompt and delayed signal because it's the neutron lithium capture signal is very localized in the energy and PSD parameter plane. And this is only our first level of IBD selection by time coincidence to make sure we subtract the background as much as possible on the Earth's surface. We exclude the prompt signal that contains nuclear recoil-like events, and the veto event, and we also veto events that coincident with cosmogenic neutron and muons and require proximity between the positron and neutron signals, and we reject the events outside of the fiducial volume of the detector because they are more accidental, higher accidental rates. With these IBD selection strategy and more than 90 days of reactor on and 70 days of reactor off, we have collected 50,000 IBD signals in the range of 0.8 to 7.2 MeV. That's about 530 IBD signal per calendar day on the Earth's surface. And we have a signal to background ratio in this energy range above 1. And we see the signal follows R over 1 over R squared trend throughout with increasing baseline. The cosmogenic neutron introducing the NH and NC star interactions, the neutron inelastic scattering interactions are the main background sources. And we recently posted these the analysis based on these data set and has submitted to PRD. With this new data set, we proceed our search for the stereo neutrino. What we do is we compare the spectra that's measured by 10 different baselines in the detector and compare these spectra to the full detector measured spectrum. And you might notice there are excluded segments in this 2D plot. It's the segments that excluded where there are PMTs with unstable response that were turned off. And this is our measurement when we compare the spectrum of each baseline to the spectrum measured by the full detector. And from these data, we don't see obvious deviation compared with the no oscillation scenario. But precisely speaking, did we see a stereo neutrino? We use Feldman-Cousin frequencies test and Gaussian CLS method to evaluate the excluded oscillation space phase. What we did is we compared the no oscillation scenario and the reactor antineutrino anomalies best fit scenario to the to our best fit data point, and our frequencies test shows the no oscillation follows a good chi-square distribution, and it's compatible with the no oscillation hypothesis at of 57%. And the reactor antineutrino anomaly, however, these parameters are excluded at 98.5%. That's 2.5 sigma. Continue with the spectrum analysis. The statistics of these new data has increased. Has been increased by 45%. compared to our previous PRL publication. And this mirrored spectrum is compared to a Huber model with a modification of a prospect mirrored non-fuel antineutrino non-fuel antineutrino contribution and a non-equilibrium fission process. Compared to this model, we find the chi-square over NDF is 3.8 over 31, 30.8 over 31. That's indicating a good data to model comparison. And so far, we are still, our uncertainty is still statistics dominated. To answer the question of did we see the bump, we did a bump dialing analysis where we added a Gaussian feature to the Huber-Muller model where Diabay experiment compared against and find the best fit Gaussian against the Diabay spectrum. And then apply this best fit Gaussian to the Huber U235 model and allow the amplitude to float to feed the prospect spectrum. And the best fit shows the best fit Gaussian amplitude is 84% plus or minus 39% compared to Diabase bump. That means we favor the hypothesis that all isotope equally contributed to the bump, and disfavor the hypothesis where neutrino no U235 contribution or all U235 contribution to that bump. So we hit the summary. The prospect reactor, the prospect's newly published data has increased our sensitivity in the high delta M square regime. To date, no evidence of stereo neutrino oscillation has been found, and we disfavor the RAA best fit at 2.5 sigma. Prospect mirror has increased the spectrum mirror and statistics as well, and compared to the LEU experiment, the result shows we suggest the hypothesis that the spectrum mismodeling is present in all fission isotope, and compare and we disfavor the no uranium-235 spectrum contribution or the only uranium-235 contribution with the 2.2 sigma and 2.4 sigma respectively. And we also started joint spectrum analysis with the stereo collaboration, and I hope you stay tuned for our update coming soon. Thank you very much.
Thank you very much for very interesting results. And we are looking forward to the next results. The next, so there are two raised hands. First is from Mikhail Danilov.
I have a question about slide number 8. In 1 over R dependence, there is a large spread of points. What is the reason for this?
That you mean the large spread point is the segments of each data point represents a segment in the detector, and I wouldn't say it's a large spreaded because each segment has a different a single segment has a may have different statistics uncertainty compared to the other segment. their position is spreaded based on how far they are from the detector, and each single segment can be at a different baseline.
But the chi-square should be quite bad in this plot.
I didn't include that value, but it really is not.
Okay, thank you.
I think it's an important topic. So there is one more question possible. So Beda, please.
Yeah, hi, thank you for a very interesting talk. I have a question about this combined analysis with stereo experiment. Can you comment on this? What exactly do you plan to achieve? What is like the outcome of this analysis? Because stereo is also on the research, like the measure only 1, 2, 3, 5. So you want to like benchmark things, or yeah, essentially what is the outcome? What we can expect from this combination then from the single experimental measurements?
A simple answer is that we want to improve our result of the spectrum analysis statistically, and also have a stronger has a stronger result when talking about the 5-MeV access with less uncertainty, and the ultimate goal is to have a better is to provide a more precise result of about the isotopic source of the spectrum deviation.
Yeah. Okay. Okay. Thank you.
Thanks again, and let's continue with the next talk by Wei Chin.
Hey, can you hear me?
Wenchin Xu talking about Majorana demonstrator, please.
Okay, thank you. I would like to thank the organizers for the opportunity to talk about the status and the recent result from Majorana demonstrator. So what we are looking at is neutrino's double beta decay, and in a regular double beta decay, you will have these two anti-neutrinos coming out of the decay. And this is possible when energetically favored. For example, this Gemini 76 decay here. In a neutrinoless double beta decay, there will be 0 neutrino coming out. And this will require an anti-neutrino to be also a neutrino, which means the neutrinos are Majorana particles. And this process violated the total number by 2 units. So what we do is really a test of total number conservation or violation. In Majorana demonstrator, we use high purity Gemini detectors to do this. There are a lot of advantages of such detectors. For example, the source is also the detector. We have an array of p-type point contact detectors, 30 kilograms of which are enriched in Gemini 76 at 88%. That is the isotope of interest. At the same time, we have demonstrated the best energy resolution in all double beta decay experiments. That is about approaching 0.1% at the Q value. And we have strategies to get no background. For example, we have compact graded shields. You can see net shield, copper shield here, and we have active muon veto and ultra clean materials. Here is a photo of our detectors to be installed. And we are operate at the underground lab. So we choose the PBC detectors because they offer more strategies dealing with background. They are intrinsically pure because of the physical and chemical processing. You can protect them from cosmic activation by limiting above ground exposure. And they have this feature of slow drift for the charge carriers that allow us to well separate multiple energy depositions inside a detector. So each individual detector is relatively small, but it is very unlikely two double beta decay can happen in one detector simultaneously. Therefore, any event with two detectors firing like this is a background event. Also, this P type point contactor result in a very localized weighting potential, which means you have the slow drift of charge carriers, which is good for pulse shape discrimination of various kind. For example, we can distinguish the signal-like single-side event from the background-like multiple-side event. Due to the multiple energy depositions here, you can see there are multiple steps in this current pulse that is for the multiple-side events. That is not so in the single-side event. Therefore, we can compare the maximum amplitude of the current pulse along with the energy. We call that A versus E parameter, and we can use that to identify multiple-side background event. We do have a population of known single-side event because of the double escape for events of the high energy gammas from the calibration source. So we can keep 90% of such double escape events, which means we have a 90% efficiency for the signal. In the end, we can achieve a factor of 3 background rejection. We have improved this A versus E parameter recently. For example, we have aligned it much better across different channels, which means across different detectors. This is the old one, and this is the new one. You can see it's much better aligned. And also we introduced the energy dependence correction, and this improves the single site acceptance at higher energy. This is due to a cobalt 56 calibration we performed. And we have noticed a correlation between the drift time of charge carriers and this A versus E parameter. This is not surprising, and we adjusted for this correction. So in the end, this new parameter is much stable and uniform across all detectors, and is a better parameter. So alpha particles can always be a problem in this business. If alpha particles deposit their energy on the passivated surface of our detectors, some of the energy could be lost. Some charge carriers could diffuse out of the surface and then drift towards the point contact with reduced mobility. So this is problematic because of the degraded energy. However, such events are much slower. If you look at the wave form after the rising edge, you can notice this characteristic slower recovery time for the surface alpha event in red, compared with rather a faster normal bulk event. So based on the slope in this region, we devised this DCR cut. And we can tune this cut based on the calibration data to retain 99% of the beta gamma events. Those are the bulk events. So you can find more details about this cut in this new paper on the archive. And we have done improvements to DCR similar to previous A versus E. So here we also aligned it better across different channels. And there is also a correlation between drift time and the DCR parameter due to charge trapping. We corrected for that as well. And we have implemented the electronics transfer function. So that also improves this parameter and provide better discrimination between the bulk events and the alpha events. Energy is really key in this business. We have the best energy resolution. We also have a record good linearity that is smaller than 0.2 keV for up to 3 MeV. On this in this new paper on archive, you can find details about our dedicated nonlinearity correction. And we also improved our energy meter recently. And with start time, we actually corrected that start time to make sure it is the same for coincidental gammas. So that is the improvement, and that reduces the residue in the energy calibration by quite a lot. This is improved energy. This is the previous one. You can see it's much improved. And this is very important, especially at a low energy. Here are some results from the demonstrator. We have had the initial result with a 10 kilogram year data, and then followed by a 26 kilogram year exposure. And that had significant blend data. That data set had a sensitivity of 4.8 times 10 to the 25th year with an observed limit of 2.7. That is because there is an event very close to the Q value, but that is still consistent with the background estimation. Right now, we are working on a new result with double the exposure and all the analysis improvements I just mentioned. We expect this in this fall. So we do have some excess of background near Q beta beta compared to our assay prediction. And we have done a lot of background modeling to understand this. Our work indicated that the excess is probably due to a source of excess thorium far away from the detectors. So it's a distant component, not anything nearby. And this can be inferred by the peak intensity and the coincidence studies. And we are still working on improving this background model. I wanted to bring your attention to the detector upgrade we have done. So we have had a number of bad channels, and that motivated the upgrade. The upgrade took place early this year and stopped by the COVID and just resumed recently. We used this opportunity to remove 5 PPC detectors from Majorana and ship them to Negin 200 for test in liquid argon. This is very important for Negin 200. And as I said, we have better cables with collectors, so we swapped out the signal and high voltage cables with much improved collectors. We also use this opportunity to install extra shielding. So you can see in this picture, this is the cross arm, and we added those additional plates to shield against the distance radiation. Last but not least, we installed 4 Alltech inverted coaxial point of contact detectors. You can see them here. They are bigger and they are intended for Negin 200. We installed them here in module 2 of Majorana to test them in our no background setup. So this is also important for Negin 200. After the upgrade, we found that all of the signal and high voltage channels are working, and all detectors are operational in module 2. So this is a great success. And we are going to run in this setup for the next half year or so to understand the performance and the background, and to reach exposure of 65 kilogram a year. Anything we learn with ICPC will be very important for Negin 200. And we are going to ship our enriched detectors to Negin 200 and continue to study our background with natural detectors. At the same time, we are making progresses on other fronts. For example, we are searching for double beta decay to excited states. This could be a good test for nuclear matrix element calculation and could be sensitive to beyond standard model neutrino properties. Due to the nature of excited states, there will be characteristic gammas when they de-excite. So essentially what we do is to look for those very sharp characteristic gammas in coincidence with those 2 electrons. And we can do that pretty well at Majorana, thanks to our greater energy resolution and no background. For example, in this simulation on the left, you can see these 2 gammas can be identified clearly, and our background is relatively low. So we found the number of events consistent with the background, and we established a stringent limit for this mode and many other modes as well. So our limits are much better than previous result. And this is also thanks to the fact that we operate in vacuum, not in liquid argon and other things. So that increases the detection efficiency. This paper is being finalized. We are also making progresses along other fronts in the search of physics beyond standard model. Also thanks to the bunch of advantages of our detectors, we have previously established limits on dark matter, solar axions, and baryon number violation. And we are working on some of the limits. For example, here is an update based on some open data. On the left, you can see our no energy data fitted by our no energy model. It can describe the data pretty well as low as 5 keV. It includes helium decay, for example, and we are still improving this. Now coming back to double beta decay, This plot shows a 3 sigma discovery level with a function of exposure. So in order to cover the inverted ordering here, you really need an exposure of 10 times a year, like this, and with extremely low background level. You can see those are different background levels, and they are really different here in this discovery plot. So we need a background that is even better than this. From the germanium perspective, this would be the large enriched germanium experiment for neutrino double-barrel decay legend. So there will be several presentations related to legend, including this talk about one of the background element. The goal of legend is to have a discovery potential at a half-life beyond 10 to the 28 years. And we wanted to use existing resources to speed up this process. That's why we are building the first phase of legend in existing infrastructure at LNGS with upgrades. This first phase is called legend 200 because we have 200 kilograms of detectors, and it has only a moderate goal for background. This is only a factor of 3, also better than good achieved background. And we hope to start data taking next year. Ultimately, we wanted to reach the legend 1000 phase with 1000 kilograms of detectors and a much more aggressive background goal. The location is to be selected, and there are a lot of R&D work ongoing. As I mentioned, some of them are at Myrona. So as a summary of my talk, we have established the limit on double-barrel decay. We have demonstrated the best energy resolution of all neutrino double-barrel decay experiments. We have been working on our background model and have learned a lot from it. We are in the process of finalizing improvements to our analysis cards, and we look forward to a new release of data in this fall. At the same time, we have been making progresses in other analyses, including excited state search and dark matter searches. So there will be a lot of results coming out of this. We are in the process of completing an upgrade to the cables and collectors, which has been really successful. The module is ready to be moved back to the shield. That would conclude the upgrade. At the same time, we deployed the new ICPC detectors for legend, and this is going to be very informative for the legend R&D. For Myrona, we expect to reach a 65 kilogram a year exposure with a sensitivity in the region of 10 to the 26 year. So please keep tuned to our result, and this is our collaboration. Thank you very much.
Thank you very much for a nice talk, and congratulations to beautiful results. I don't see any hands raised, so I take the privilege to ask a question. I would like to know, you are talking about the thorium as the main source of the background. Where is the thorium located in the experiment, and what is the origin?
Right, so when we say the thorium is the main thing, we are talking about an excess in comparison with our assay model. And right now, what we can say is that this excess of thorium in comparison with assay is coming from far away component. For example, some component in this area could be possible. We can conclude that it is unlikely to coming from nearby parts, such as the detector holders and any other things close to the detectors. So it's a very general statement, and that's learned by looking at the different peak ratios and coincidence. The background is in general very low, so it's actually a little bit difficult to pin down a particular source.
Thank you. Well, I don't see any other questions. So thanks to all speakers. It was a very interesting session today. And the session is closed.
Thank you. Bye.